Geological catastrophes are powerful events that can fundamentally alter the face of our planet. During their occurrence, Earth demonstrates its strength as nature shuffles the cards, creating new landscapes and ecosystems. These catastrophes typically occur on a scale that exceeds human perception of time. They can take millions of years, but their manifestations, such as volcanic eruptions, earthquakes, or tsunamis, are mere moments in the billions of years of Earth's history. Scientists studying geological time assert that the platform we live on is approximately 4.5 billion years old. In this context, catastrophes are not just destructions, but rather part of cycles that lead to new forms of life and the evolution of existing ecosystems. For example, after a major mass extinction event that occurred around 65 million years ago, a new period began on Earth, leading to the flourishing of mammals and, ultimately, the emergence of humans. These events, though dramatic, only underscore the grandeur and strength of nature, which can restore and adapt. Geologists and paleontologists study rock layers to understand how different catastrophes have influenced the formation of continents and oceans. For instance, in some places on Earth, one can observe layers formed by ancient floods that left behind rich deposits, fostering the emergence of new life forms. Volcanic eruptions, such as the one on the island of Crete around 3,000 years ago, led to the creation of fertile soils that contributed to the development of ancient Greek civilization. Scientists emphasize that each catastrophe, although destructive, always creates conditions for new beginnings. In this sense, Earth resembles an artist who, with a bold stroke of the brush, changes a painting, creating new forms and colors. The degree of destruction should not be feared, as it inevitably leads to the birth of new life. For example, a study conducted in 1991 showed that after the eruption of Mount St. Helens, new flora and fauna that appeared on the devastated areas were significantly more diverse than before the catastrophe. All this confirms that Earth is not just a static object, but a dynamic system capable of self-restoration and transformation. Geological catastrophes, even the most massive, are perceived as a natural part of the long and slow flow of geological time, where each moment of destruction is also a moment of creation and renewal. The study of ancient life forms, such as trilobites, which went extinct around 250 million years ago, helps understand how life adapted to changing conditions on the planet. These organisms witnessed numerous catastrophes that led to the formation of new ecosystems, and their fossils serve as important evidence of the changes that occurred on Earth. It is important to understand that geological catastrophes are not just tragedies, but significant stages in the history of our planet, highlighting its ability to restore and evolve. Each layer of the Earth, each fossilized remnant, is not only a testament to the past, but also a key to understanding future changes. Thus, Earth continues its eternal cycle, in which catastrophes, like lightning piercing the sky, illuminate not only the darkness, but also the path to new possibilities and forms of life. The formation of Earth began around 4.5 billion years ago from a vast cloud of gas and dust composed of hydrogen, helium, and heavy elements expelled into space by supernova explosions. In this cloud, particles gradually began to coalesce due to gravity, forming increasingly larger clumps of matter. This process, which lasted for millions of years, involved temperatures inside the forming bodies reaching fantastic values. Constant collisions of small bodies, falling onto each other with immense force, resulted in the formation of a molten sphere. These collisions were accompanied by powerful explosions and the release of enormous amounts of energy, creating an atmosphere of primordial chaos, similar to a gigantic cosmic welding machine. Each new impact added to the mass of the future planet, and the surface temperature reached thousands of degrees Celsius, making it completely inhospitable for life. At this stage, Earth was no more than a hot, molten mass covered with oceans of magma. Due to continuous movement and collisions, Earth accumulated not only mass, but also internal energy. As particles coalesced into larger bodies, they began to form the first planetesimals, the size of mountains, which grew larger over time. This process led to the formation of the Moon when one of the large objects collided with Earth, ejecting a massive amount of material into orbit. Over millions of years, this material coalesced to form our satellite, which became an integral part of the Earth's system. Throughout this time, the atmosphere underwent numerous chemical reactions that released gases such as water vapor, carbon dioxide, and ammonia. These gases, in turn, created the primary atmosphere, protecting Earth from cosmic radiation and creating conditions for further changes. Gradually, the cooling of the surface led to the formation of the first oceans, which became the basis for the emergence of life. This process of Earth's formation is not just a story of how a planet became habitable, but also a story of how order emerged from cosmic chaos, which we observe today. Ultimately, Earth's size reached approximately 12,742 kilometers. Its mass reached about 19,300 billion tons, and the temperature in the core reached around 5,000 degrees Celsius. The formation of Earth's primary crust occurred as a result of complex cooling processes that began approximately 30 million years after the planet's formation. During this period, the surface, which had reached temperatures of 6,000 degrees Celsius, began to slowly cool, creating the first thin layers of solid shell. A key aspect of this process was the uneven formation of the crust. Due to intense volcanic activity and tectonic movements, the surface was constantly torn apart and reformed. Internal forces of the planet, such as the movement of magma and gases, pushed lava to the surface, which then cooled to form basaltic rocks. Around 300 million years after Earth's formation, when cooling reached a critical point, a crust composed of complex minerals such as plagioclase, pyroxene, and olivine formed. At this point, the surface no longer glowed with the light of molten rock, and Earth entered a period of darkness where the first continents began to take shape. The fragility of this primary crust was evident. Even minor changes in temperature or pressure could cause its destruction, as evidenced by geological findings of ancient fault lines in samples of crust older than 3 billion years. The crust was not only thin, but also unstable, with a thickness ranging from 5 to 30 kilometers, making it vulnerable to subsequent geological changes. These changes included the formation of oceans that filled lowlands and active volcanic eruptions that continued to shape landscapes. Scientific research indicates that around 2 billion years ago, the crust began to stabilize, allowing the formation of continents as we know them today. These primary continents were not like modern ones. They had high mountain ranges formed by the collision of tectonic plates and vast plains covered with volcanic rocks. Scientific research shows that the primary crust of Earth was the foundation for future geological processes that led to the creation of diverse ecosystems and ultimately life. The initial crust, composed of silicates and other minerals, was merely the first stage in the evolution of our planet. Proto-Earth, which formed around 4.5 billion years ago, collided with the planet Theia in an event that became one of the most significant in the history of the solar system. Theia, named after the ancient Greek goddess, was a celestial body the size of Mars and was in orbit that intersected with the orbit of Proto-Earth. This colossal impact occurred approximately 30 million years after the formation of the solar system. The two cosmic bodies approached each other in a slow but inexorable dance, their orbits gradually intersecting, creating tension that ultimately resulted in a catastrophic collision. The energy of the impact was equivalent to the explosion of several million atomic bombs, leading to the formation of a cloud of hot gases and debris. As a result of this collision, part of the mantle and crust of Proto-Earth was ejected into orbit, forming a disk of gas and dust around the young planet. These materials, consisting of silicates and metallic particles, orbited in the orbital paths, gradually coalescing into larger objects. Over millions of years, due to gravitational attraction, these debris came together, forming the Moon. The Moon's mass was approximately 1/8 of the mass of Earth, and its gravitational influence had a significant impact on Earth's processes. The impact process was not only destructive, but also remarkably graceful. The debris, as they orbited, created magnificent light effects, reflecting sunlight and forming bright rings that could rival those of Saturn. This cosmic ballet ended with the creation of a satellite that witnessed the formation of oceans and continents on Earth. Scientists suggest that it was precisely this collision that created conditions on Earth conducive to the emergence of life. The Moon, located at a distance of approximately 380,000 kilometers from Earth, stabilized its axis of rotation, contributing to climatic stability. The collision with Theia was not just a catastrophe, but a powerful driver of evolutionary processes on our planet. Around 7 billion years ago, when Earth and the Moon began their long shared history, the first simplest forms of life began to appear on Earth, which later evolved into complex organisms. As a result of the collision between Earth and Theia, a vast cloud of debris was formed, consisting of molten and suspended particles that began to slowly coalesce into a single entity. In the first tens of thousands of years after the catastrophe, these particles, orbiting around Earth, collided with each other, contributing to their aggregation. Each new encounter between particles led to the formation of increasingly larger clumps, which eventually accumulated, forming a protoluna. Approximately 100 million years later, around 3 million years after the collision, due to gravitational attraction and subsequent collisions, the mass of these debris became large enough to begin taking the shape of a more stable celestial body. The process of lunar formation continued for several tens of millions of years, and by this time its crust had formed, with molten mantle layers beneath. This was the process of the birth of a satellite that would not only become a faithful companion of Earth, but also a crucial factor influencing its life. The Moon, with a diameter of about 3,400 kilometers, had a significant impact on the atmosphere and climate of our planet. Its gravity initiated tides, which in turn facilitated the development of the first living organisms in the oceans. Tides reaching heights of more than 10 meters in some places created unique ecosystems where life could develop and evolve. The Moon also slowed down the rotation of Earth, leading to a more stable climatic system and easing the conditions for the appearance and survival of various forms of life. Over billions of years, the Moon remained an unchanging companion, and its gravitational influence continued to shape the rhythms of life on Earth. Throughout different periods of its existence, the Moon was subjected to meteorite bombardment, leaving numerous craters on its surface, which testify to its tumultuous history. These craters, such as the Tycho crater, with a diameter of about 150 kilometers, are the result of powerful collisions that occurred during the early formation of the solar system. Each of these craters tells a story about how the Moon interacted with the cosmos surrounding it. The lunar landscape, covered with regolith created from small particles and volcanic formations, is a reflection of the history not only of the Moon, but also of the entire solar system. Thus, the Moon became not just a satellite, but a significant participant in the evolution of life on Earth, influencing its climate, ecosystems, and even the behavior of living beings. In its early stages of existence, Earth was subjected to constant bombardment by meteors and asteroids, leading to what is known as the Late Heavy Bombardment period. These catastrophic collisions occurred over millions of years, creating lunar landscapes characterized by deep craters and mountains on the planet's surface. Each impact was not just a destruction, but also a catalyst for the formation of new geological structures. For instance, when a meteor struck Earth, it released energy equivalent to millions of atomic bombs, resulting in the formation of craters up to tens of kilometers in diameter and the ejection of vast quantities of dust and gas into the atmosphere. These materials, rising into the atmosphere, could block sunlight, thereby altering the planet's climatic conditions. As a result of these impacts, new conditions were created for the emergence and evolution of life. Oceans formed due to volcanic activity and the melting of ice, becoming habitats for the first living organisms. These organisms, in turn, formed the basis for more complex ecosystems that developed on the planet's surface and in its waters. The diversity of landscapes created by these constant changes provided unique conditions for the evolution of living beings. Mountains, plains, and oceans, formed as a result of these cosmic impacts, became not just geographical features, but also key elements in the further development of the biosphere. Nature used each impact as an opportunity to create new ecosystems, leading to the diversity of life forms we observe today. These processes occurred against the backdrop of a constantly changing climate, driven by volcanic activity and gas emissions, creating a dynamic environment for all living beings. As a result, Earth, having experienced such catastrophes, became a place where life could take root and adapt to changing conditions. In the early stages of the planet's development, when continents and oceans were forming, each new geological structure opened up new possibilities for life. After each impact, new minerals and materials were created, adding diversity to the ecosystems. These factors not only contributed to the survival, but also to the evolution of organisms that adapted to new conditions. Complex interactions between climate, geological processes, and biological communities formed the basis for the development of our planet as a unique system where life could thrive. Each collision with cosmic bodies left its mark in the form of new landforms, altering the appearance of Earth and contributing to the development of life. Ultimately, it was these cosmic catastrophes that gave Earth its current appearance and made its history one of the most fascinating tales of survival and adaptation in the face of constant change. Impact craters formed as a result of these collisions became important indicators for studying the cosmic history of our planet. The atmosphere of the ancient Earth was vastly different from what we observe today. Around 4 billion years ago, the air was saturated with heavy gases such as carbon dioxide, ammonia, and methane. The concentration of oxygen was so negligible that the life we know today was impossible. Instead of the familiar blue sky overhead, there was a reddish, sometimes even brownish glow, caused by the action of sunlight on the gas molecules in the atmosphere. This glow, reminiscent of a sunset's glow, was created by complex chemical reactions taking place in the atmosphere, where oxides and other compounds dominated, reflecting and refracting light. Electric discharges resulting from frequent thunderstorms added an alien and dangerous feel to this world. Scientists like Dr. David Lane from the University of California claim that these discharges could have played a crucial role in the formation of organic molecules necessary for the emergence of life. Nevertheless, this atmosphere, filled with toxic gases and constant electrical discharges, was truly hostile to any forms of life that might have existed. Surface temperatures could reach up to 150 degrees Celsius, and the air was filled with clouds of sulfuric acid, formed due to high concentrations of sulfur dioxide. These conditions were such that even the simplest microorganisms that might appear later had no chance of survival. However, it was precisely in these conditions that the most important chemical processes took place, ultimately leading to the formation of the first simplest forms of life. For billions of years, this world remained barren and lifeless. But within its depths, the foundations for future development were already being laid. Periodically, comets and meteoroids struck the Earth, carrying water and organic compounds. These celestial bodies could have acted as catalysts for the creation of the first molecules necessary for the emergence of life. Thus, despite its hostile atmosphere, ancient Earth already harbored the potential for biological processes that would later transform its appearance. The structure of the atmosphere was not only dense, but also dynamic. Temperature fluctuations and changes in chemical composition caused constant changes in meteorological conditions. These conditions shaped the landscape, gradually creating conditions for future oceans that could become the cradle of life. Geologists like Dr. Kate Kerr assert that these early oceans, formed from the condensation of water vapor, became the basis for the creation of the first cells. Each of these processes occurring in the atmosphere was part of a long path towards the emergence of life. This was an era when the planet was in a state of constant transformation, and each molecule, each change, formed invisible bonds that determined the further destiny of the Earth. Ultimately, it was in this seemingly inhospitable atmosphere, where heavy gases and electrical discharges prevailed, that the foundations for the future diversity of living beings were laid. The atmosphere of ancient Earth, filled with toxic gases created by volcanic activity, did not give a chance for the existence of familiar life. But in this chaos, important chemical reactions also took place, which became the basis for life. Underwater volcanoes ejected rich mineral substances, creating conditions for the appearance of the first living organisms. From the depths of space, comets and asteroids brought ice and water vapor, which over time filled the lowlands of the planet, forming the primary oceans. This happened approximately 4 billion years ago, when Earth was just beginning to form as a planet capable of supporting life. The water that came from the heavens was not ordinary. It contained numerous minerals and chemical substances such as sodium, calcium, and magnesium, which upon dissolving created a unique composition of the primary oceans. The color of this water varied from dark blue to greenish, depending on the concentration of dissolved substances and the presence of organic compounds. Research shows that the primary oceans were not only filled with ordinary water, but also with complex organic molecules that formed as a result of chemical reactions under the influence of ultraviolet radiation and electrical discharges. This led to the formation of amino acids and other biomolecules necessary for the origin of life. Scientists such as Stanley Miller and Harold Urey in their experiments in the mid-20th century demonstrated that such molecules could arise under conditions similar to the primitive Earth, when they were subjected to electrical discharges in a mixture of gases mimicking the atmosphere of that time. The water in these oceans was not pure. It had a high concentration of minerals, making it a chemically active environment for further biochemical processes. These primary oceans became the place where complex chemical reactions occurred, leading to the formation of the first simplest organisms. Evidence of these early forms of life was found in the form of stromatolites, fossilized remains left by ancient microorganisms that lived more than 3 billion years ago. These fossils contain traces of photosynthetic bacteria that began to release oxygen into the atmosphere, which in turn changed the climate and composition of the Earth's atmosphere, creating conditions for more complex forms of life. It is important to note that the primary oceans not only filled the lowlands of the planet, but also became the cradle for biochemical processes that later led to the appearance of diverse life forms that we observe today. The Earth's crust is composed of several large and small sections, known as plates, which slowly move across the planet's surface. This process, known as plate tectonics, has been ongoing for millions of years and is fundamental to the formation of various geological structures, such as mountains, oceans, and earthquakes. Each plate has its own speed of movement, ranging from several millimeters to several centimeters per year. While this may seem insignificant to humans on a geological timescale, these changes result in significant landscape transformations. For instance, the collision of plates can lead to the uplift of mountain ranges, such as the Himalayas, which began to form more than 45 million years ago. The formation of mountains occurs as a result of complex interactions between plates, including subduction, where one plate moves under another, leading to the creation of deep oceanic trenches and volcanic activity. There are also zones of extension where plates spread apart, creating new oceanic floors and resulting in the formation of geological structures like mid-ocean ridges. Throughout Earth's geological history, numerous changes have shaped continents and oceans into their current forms. Around 200 million years ago, all continents were united into the supercontinent Pangaea, which gradually broke apart into the modern continents. This process continues, and according to some models, continents may reunite into a new supercontinent within the next 100 million years. Plate tectonics is also responsible for the occurrence of earthquakes and volcanic activity, which result from stresses in the Earth's crust. For example, numerous large earthquakes were recorded in the 20th century, such as the San Francisco earthquake in 1906, which caused significant damage and loss of life. Interestingly, plate tectonics not only influences geological processes, but also affects climatic conditions, as changes in the location of continents can alter ocean currents and atmospheric flows, which in turn affect climate zones. Therefore, plate tectonics is not just a process that shapes landscapes, but a complex system of interactions that has transformed our planet over billions of years. Each year, numerous small changes occur, ultimately leading to global transformations, demonstrating how the slow but steady movement of plates shapes the face of the Earth. In this context, it is worth noting that scientists continue to study the mechanisms behind plate tectonics and their impact on life on the planet. For instance, a study by a group of geologists from the University of California, Berkeley, showed that tectonic processes may be linked to changes in the biosphere and the evolution of living organisms, highlighting the complexity of interactions between geological and biological systems. Subduction is a process in which one tectonic plate slowly descends beneath another, returning to the Earth's mantle. This process occurs in areas known as subduction zones, where oceanic and continental plates meet. For example, on the western coast of South America, the Nazca Oceanic Plate is subducting beneath the South American continental plate, creating a powerful subduction zone known as the Andes system. During this process, tension builds between the plates over decades or even centuries. This tension leads to an increase in pressure at the plate boundary, where friction between the plates hinders free movement. When the tension reaches a critical point, there is a sudden release of energy, causing earthquakes. For instance, the earthquake in Chile in 1985, one of the most powerful in history, reached a magnitude of 9.5, and its epicenter was near the boundary of the oceanic and continental plates. This event resulted in significant damage and loss of life. Additionally, in subduction zones, volcanoes often form because the descending plate releases water and other volatile substances, lowering the melting point of mantle rocks. This results in the formation of magma chambers that can lead to volcanic eruptions, such as the Cotopaxi volcano in Ecuador, which is located near a subduction zone. These processes highlight how plate interactions can influence regional geological activity and shape the landscapes we see today. Subduction also plays a crucial role in understanding Earth's geological cycles, as it is key to the redistribution of elements and minerals in the Earth's crust. Approximately 70% of known volcanic activity is related to subduction. Each year, hundreds of earthquakes occur at plate boundaries, and even small changes in tectonic processes can have serious consequences for the environment and human populations. For example, a study conducted in 2020 by a group of scientists from the University of Tokyo showed that even small changes in the speed of subduction can lead to significant changes in volcanic activity and the frequency of earthquakes. These observations emphasize the importance of monitoring tectonic activity and understanding the processes occurring at deep levels within the Earth. Subduction is not just a geological process, it is a dynamic system in which forces interact, capable of altering the appearance of entire continents and creating new geographical forms, such as mountain ranges. Seafloor spreading is a process that occurs in the oceanic crust at the boundaries of oceanic plates, where magma rises from the Earth's mantle and creates new oceanic crust. This process begins at mid-ocean ridges, such as the Mid-Ocean Ridge, which stretches over more than 16,000 kilometers along the floor of the Atlantic Ocean. In these areas, where tectonic plates are moving apart, magma from deep within the Earth's interior penetrates through cracks formed by the movement of the plates. The temperature of this magma can reach around 1,000 degrees Celsius, and as soon as it reaches the surface, it quickly cools to form basaltic rock. Seafloor spreading can be observed in real time. For example, in the 1970s, a team of researchers led by Dr. Robert Craig from the University of California, Santa Barbara, studied the activity in the area around Haiti and discovered that new underwater volcanoes had formed. These volcanoes, which form in complete darkness and high pressure, not only eject basalt, but also a variety of gases, such as carbon dioxide and hydrogen sulfide, creating unique underwater ecosystems. Magma rising from the Earth's interior can also form new mountain ranges. It slowly pushes continents apart, sometimes at a rate of just a few centimeters per year. This movement leads to the formation of new ocean basins and changes in the landscape. For instance, the process of spreading in the Atlantic Ocean, which began more than 100 million years ago, caused continents such as South America and Africa to move apart, creating the modern appearance of the Earth. It is interesting that on the ocean floor, there are hydrothermal vents formed by the interaction of magma and seawater. These vents, known as black smokers, release minerals that create unique ecosystems inhabited by organisms capable of surviving in extreme conditions. Such organisms as tube worms and bacteria use sulfur as a source of energy, highlighting the diversity of life in the most remote corners of our planet. Seafloor spreading is also linked to the formation of new rifts and faults, which can be sources of earthquakes. For example, in 1994, an earthquake with a magnitude of 6.8 occurred in California, and its epicenter was near the San Andreas Fault. This underscores that processes of seafloor spreading not only form new crust, but can also cause catastrophic natural phenomena. Therefore, the process of seafloor spreading is not just the movement of continents. It is a complex and dynamic system in which underwater volcanism, new ecosystems, and tectonic activity interact with each other. These processes continue to shape our planet, creating new geographical forms and altering marine landscapes. The height of underwater volcanoes can reach several kilometers, and they constitute a significant part of the Earth's total mass. Supercontinents are vast landmasses that form and break apart over geological epochs. These processes occur approximately every 300 million years, resulting in cycles of continental unification and separation on Earth. When supercontinents unite, they create extensive ecosystems and influence climatic conditions. For instance, the joining of landmasses can lead to the formation of vast internal seas and alterations in atmospheric currents, which in turn affect precipitation and temperature in various regions. During these periods, when the Earth's surface is a single continent, there is intense species migration, contributing to biodiversity. The union of landmasses creates bridges between ecosystems, allowing different species to move and adapt to new conditions. However, over millions of years, continents begin to separate, leading to the isolation of ecosystems. This process can result in the evolution of unique species that adapt to the new, isolated conditions. For example, when continents divide, isolated populations begin to develop independently, leading to the creation of new species. The division of land masses also alters oceanic currents, which influence the distribution of heat in the oceans and consequently the climate of Earth. Currents such as the Gulf Stream are formed due to the position of continents and affect the climate in northern and southern latitudes. When continents are in different positions, oceanic currents can weaken or strengthen, changing the temperature of seas and influencing weather patterns. Over millions of years, this process creates unique conditions for life, leading to the emergence and disappearance of entire ecosystems. For example, during the formation of a supercontinent that existed around 300 million years ago, there was a significant change in the composition of flora and fauna, as species previously on different continents began to interact. These interactions create new ecological niches and alter the dynamics of ecosystems. As a result, we see how life on Earth changes in response to tectonic processes that can take millions of years. During the breakdown of supercontinents, new oceans form, leading to the creation of new coastlines and changes in the landscape. For instance, the formation of the Atlantic Ocean, which began around 100 million years ago, resulted in significant changes in the distribution of species and ecosystems. This process continues today, making our planet dynamic and ever-changing. Supercontinents are not just geological formations. They represent the living history of Earth, where each stage of unification and separation influences the climate and life on the planet. As a result of these processes, continents can be in various states of isolation and connection, creating conditions for evolution and biodiversity. For example, during the last ice age, which ended around 10,000 years ago, significant climate changes occurred due to the movement of continents and changes in oceanic currents. These changes influenced the migration of humans and animals, contributing to the formation of new ecosystems. Therefore, supercontinents play a crucial role in the evolution of Earth and its life. Supercontinent Pangaea formed around 300 million years ago at the end of the Paleozoic era and existed until around 200 million years ago. When its disintegration began, Pangaea was a gigantic continent that occupied almost the entire landmass of the planet, stretching in the shape of the letter C and surrounded by the ocean Panthalassa. This continent was unique not only in its shape, but also in its climatic conditions, which prevailed on it. The interior parts of Pangaea were extremely arid, forming vast deserts, as the distance from the coasts to the center of the continent was significant, preventing oceanic moist winds from reaching the interior territories. At the same time, on the coasts of Pangaea, monsoon climatic conditions prevailed, creating rainfall cycles, but these regions were limited to narrow strips surrounding the continent. The average temperature on Pangaea could reach 30 degrees Celsius in the summer months, while in the winter, in the central regions, it could drop to -10 degrees. The absence of moderate climatic zones on most of the landmass led to the fact that the ecosystems of Pangaea were quite specific, with the prevalence of tropical and subtropical plants, such as giant ferns and coniferous trees. Interestingly, such climatic conditions contributed to the formation of enormous coal deposits, which are now an important part of the energy infrastructure of many countries. While tropical forests grew on the coasts, the internal desert regions were harsh conditions for life, where survival was possible only for the most hardy plant and animal species. Pangaea also became the habitat for numerous dinosaurs and other reptiles, which adapted to various climatic conditions. For example, in the more humid coastal zones, species such as Plateosaurus inhabited, while in the arid interior regions, more adapted to harsh conditions, species dominated. These climatic features not only influenced the distribution of biological species, but also caused numerous migrations of animals and plants as the continent began to break apart. Approximately 180 million years ago, Pangaea began to disintegrate into parts, which in turn changed the climatic conditions on Earth, creating new ecosystems. Thus, Pangaea was not only a geographical formation, but also a significant milestone in the history of the Earth, influencing the development of life on the planet. At this time, the continent lacked significant mountain ranges that could affect the climate, making it unique in its own way. Scientific research shows that it was during this period that numerous changes in the composition of the atmosphere and oceans occurred on Earth, which in the end became the basis for future biodiversity. The formation of Pangaea and its subsequent disintegration opened new horizons for evolution, which continue to influence the biosphere to this day. The process of Pangaea's disintegration began approximately 100 million years ago, when a single supercontinent covering almost a quarter of Earth's surface began to slowly tear apart. This process was caused by the movement of tectonic plates that lie on Earth's surface and move due to convection currents in the mantle. Initially, continents began to separate from each other, forming narrow straits that gradually widened. The first significant event in this process was the formation of the Tethys Ocean, which emerged between the northern part of Pangaea, Laurasia, and the southern part, Gondwana. This ocean became a habitat for numerous marine organisms, including early dinosaurs and amphibians. Then, around 90 million years ago, Pangaea split into two large continents, Laurasia in the north and Gondwana in the south. These continents continued to move, and new oceans began to form between them, such as the Atlantic Ocean. The process of continental separation was uneven and lasted for tens of millions of years. For example, around 80 million years ago, the central part of the Atlantic Ocean began to open, as continents started to drift apart at a rate of up to 10 centimeters per year. This speed may seem small, but over millions of years, it led to the formation of vast oceans that separated continents by significant distances. On the southern side, Gondwana slowly broke apart into several parts, including South America, Africa, Australia, and Antarctica. Around 60 million years ago, the final separation of South America and Africa occurred. As a result of further expansion of the Atlantic Ocean, this process also led to the appearance of new seas, such as the Caribbean Sea, and altered climatic conditions in various regions. As a result, wide oceans emerged between continents, becoming homes for diverse ecosystems. By the end of the process of Pangaea's disintegration, it became one of the most significant geological events in Earth's history, determining not only the current positions of continents, but also their biological diversity. As a result of this monumental process, which lasted for millions of years, Earth acquired its modern appearance, and the oceans formed between continents became vital arteries for marine life. Scientific research shows that tectonic movements continue today, indicating the ongoing dynamism of our planet. The formation of the Atlantic Ocean is a remarkable process that began approximately 100 million years ago, when the continents we live on today began to gradually split apart and move in different directions. At the time when Gondwana, a vast supercontinent, started to break up, a narrow strait formed between Africa and South America, which later became the basis for the Atlantic Ocean. This expansion occurred due to tectonic movements of the plates, leading to the formation of new oceanic crust and active volcanic activity. Scientific research shows that during the period between 100 million and 60 million years ago, as the ocean was actively expanding, significant oceanic currents such as the Gulf Stream emerged. This warm current, originating in the Caribbean Sea, began to move northward along the eastern coast of the United States, exerting a significant influence on the climate of the North American continent. Simultaneously, cold currents like the Labrador Current formed in the north, creating unique climatic conditions that fostered the development of diverse ecosystems. As the Atlantic Ocean expanded, maritime routes also changed, profoundly affecting the evolution of marine life. The ocean became saltier and its temperature fluctuated, creating new ecological niches for various species. For example, the formation of warmer waters in the Caribbean Sea and their interaction with cold waters coming from the north led to the development of unique coral reefs, which became homes to numerous marine creatures. Research shows that during this period, which spanned the Cretaceous era, new fish and mollusk species emerged, adapting to the changing conditions. The climate on the adjacent continents also underwent changes. The increase in ocean size contributed to more moderate and humid conditions in Europe and on the eastern coast of North America. As a result of these changes, ecosystems became more diverse, and new biomes, such as deciduous forests and steppes, began to develop on the continents. The Atlantic Ocean became a key factor in global atmospheric and oceanic circulation. Over time, its expansion not only altered the geographical map, but also changed the way of life on the continents surrounding it. The discovery of new maritime routes in the 15th and 16th centuries during the age of great geographical discoveries facilitated trade and species migration, thereby increasing biological diversity. For instance, the opening of new maritime routes led to the exchange of species between the Old and New Worlds, resulting in many species originally inhabiting one ocean beginning to colonize new territories, thereby altering the local fauna and flora. Thus, the expansion of the Atlantic Ocean was not just a geological event, but also a significant step in the evolution of life on Earth, opening new horizons for marine life and shaping climatic conditions for the continents surrounding it. As a result of the interaction between the ocean and the atmosphere, unique ecosystems were formed, which continue to develop today. The average depth of the Atlantic Ocean is 3,800 meters, and its maximum depth, located in Puerto Rico, reaches 8,600 meters. Volcanism is a phenomenon associated with the movement and ejection of magma from the Earth's interior to the surface through faults in the crust. This internal energy, accumulated in the form of heat and pressure, leads to the formation of molten rock, which can ultimately erupt as lava, gases, and ash. There is a constant tension between the internal forces of the planet and its crust, which can be likened to a compressed spring. As long as the spring is not released, it maintains its shape, but when the pressure becomes too high, it can suddenly expand, releasing all the accumulated energy. The internal layers of the Earth, such as the mantle and core, are complex systems where convective processes occur, facilitating the movement of molten rocks. The temperature at the center of the Earth reaches almost 6,000 degrees Celsius, creating conditions for the melting of silicate minerals and the formation of magma. When magma rises through faults in the crust, it can accumulate in magma chambers, where pressure continues to build. As soon as the pressure reaches a critical level, magma finds an outlet, causing an eruption. Volcanism can manifest in various forms, including shield volcanoes, stratovolcanoes, and volcanic islands, which form as a result of multiple eruptions. Each eruption can expel millions of tons of material, including volcanic gases that can rise to heights of up to 30 kilometers in the atmosphere. Studying volcanic activity requires the use of modern technologies, such as seismology and satellite imagery, for monitoring earthquakes and changes in the Earth's crust that may precede eruptions. For example, in the 21st century, using GPS and other tools, scientists were able to predict several major eruptions, saving lives and minimizing damage. It is important to note that volcanism not only destroys, but also creates new lands. Volcanic islands like Hawaii were formed over many thousands of years of eruptions. These processes significantly contribute to the formation of the landscape and ecosystems of our planet, creating unique conditions for life. Volcanic activity also contributes to the formation of valuable minerals, such as sulfur, gold, and copper, which can be found near volcanoes. Each eruption leaves a trace in the geological history, forming layers of volcanic deposits that can be studied by geologists to understand the evolution of the Earth. Volcanism is not just a natural phenomenon, but a powerful process that continues to influence our planet and humanity. Trap volcanic activity is one of the most impressive processes associated with magma outflows, when a vast volume of lava is poured onto the Earth's surface, capable of covering territories over thousands of square kilometers. These outflows occur through cracks in the Earth's crust, and lava flows can spread over tens of kilometers, forming extensive plateaus. The lava, typically basaltic in composition, moves slowly and steadily, accumulating layers that over time form stepped structures known as traps. The most famous examples of trap volcanic activity can be found in India, where the Deccan traps, formed around 65 million years ago, cover more than 500,000 square kilometers. These massive eruptions occurred as a result of the Earth's lithosphere being torn apart by the rise of magma from the mantle. Lava flowing from these cracks gradually cools and solidifies, forming powerful layers that can reach tens of meters in thickness. Each new lava flow covers the previous one, creating a unique structure that can resemble enormous steps reaching towards the sky. Volcanic activity in these regions is also linked to the formation of specific ecosystems, as new lands provide habitats for plants and animals to colonize. For instance, on the Deccan traps, fossils of ancient marine creatures have been found, indicating that this area was once covered by an ocean. Volcanic eruptions can also lead to the formation of craters and other volcanic structures, significantly altering the local topography. Such changes can be so extensive that they affect the climate conditions in the region, as new landscapes can alter air currents and precipitation patterns. Over millions of years, trapped volcanic activity has not only shaped the geography of continents, but also influenced the development of life on Earth. For example, a massive eruption on the territory of modern-day western USA, known as the Columbia Plateau, occurred around 15 million years ago and left a significant mark on the planet's history. The height of lava plateaus can reach up to 1,000 meters, creating vast and inaccessible areas that become homes for diverse flora and fauna. Trap formations are often interrupted by river valleys and other geological structures, further emphasizing their scale and grandeur. Compared to conical volcanoes, traps represent a broader and less steep landscape, characteristic of large volumes and low lava viscosity. Such eruptions significantly determine not only the geological structure, but also the climate conditions that can affect ecosystems located far from the eruption site. Trap volcanic activity continues to be a subject of interest for scientists seeking to understand the processes that led to the formation of these massive geological features. Siberian traps represent one of the most significant geological formations on the planet, covering an area of over 1 million square kilometers. These massive volcanic formations began to form around 250 million years ago, at the end of the Triassic period, and continued into the Jurassic period. The main eruptions occurred over several million years, during which volcanoes ejected enormous volumes of basaltic lava that spread across modern Siberia, forming multi-kilometer layers. These eruptions were associated with rifting, when tectonic plates diverge, leading to the formation of cracks in the Earth's crust. The lava flows that form the traps are characterized by their low viscosity and large area of spread, making them unique in a geological context. Powerful gas emissions, such as carbon dioxide and sulfur dioxide, into the atmosphere created conditions conducive to global climate changes. From time to time, the sky over Siberia was darkened by volcanic ash, and sunlight barely pierced the atmosphere filled with particles and gases. These conditions led to significant temperature drops, creating what is known as a volcanic winter. According to estimates, the temperature could drop by several degrees Celsius, having catastrophic consequences for flora and fauna on the planet. For example, plants experienced stress due to lack of light, which in turn affected food chains, leading to mass extinctions of species. Scientists suggest that such climatic conditions caused by the Siberian traps could have contributed to the mass extinction at the end of the Permian period, when up to 95% of all life forms on the planet disappeared. These events highlight how powerful geological processes can influence global climate and ecosystems. The Siberian traps serve as a striking example of how volcanic activity can change not only local, but also global ecosystems. Currently, researchers continue to study the impact of these ancient eruptions by analyzing rock samples and studying the traces of volcanic activity in sedimentary layers that have been preserved for millions of years. Comparing with other large volcanic events, such as those in India, also helps to better understand how such catastrophic changes affected climatic conditions in different historical epochs. The Siberian traps are not just a geological phenomenon, they are a lesson about how nature can regulate climatic conditions on the planet. Even after millions of years, the traces of these eruptions are still visible, and their influence is felt in modern ecological systems. There is ample evidence that the Siberian traps played a decisive role in changing the biosphere of Earth, and they continue to be the subject of active research. Siberian traps had a direct impact on the Permian extinction, which occurred approximately 250 million years ago and was the largest mass extinction in Earth's history, wiping out up to 95% of all marine and 75% of terrestrial organisms. Volcanic activity associated with the formation of traps led to the release of enormous volumes of carbon dioxide and other gaseous substances, including sulfur dioxide, into the atmosphere. These gases altered the composition of the atmosphere, causing a sharp increase in the concentration of carbon dioxide, which led to the greenhouse effect and a significant rise in global temperature. According to research, the temperature on Earth could have risen by 10 degrees Celsius over several thousand years following the onset of eruptions. This climate change led to the degradation of ecosystems, as high temperatures caused droughts and altered the usual conditions for the existence of many animal and plant species. One of the most devastating consequences was the acidification of oceans, caused by the dissolution of carbon dioxide in seawater, which led to a decrease in pH from 8 to 6. This change had a detrimental effect on marine flora and fauna, particularly on organisms that use calcium to create their shells, such as mollusks and corals. Research shows that coral reefs that existed at the time began to disappear rapidly, disrupting marine ecosystems and triggering further extinctions. Scientists such as Dr. Edward D. Kay, Hale of the University of California, point out that the combination of these factors created ideal conditions for a global catastrophe that led to the extinction. Volcanic gases, including sulfur compounds, also led to the formation of acid rain, which further exacerbated the situation on land, poisoning the soil and water bodies. The decrease in the number of organisms, both terrestrial and marine, led to the disruption of food chains. This extinction was not just an ecological event, but a full-blown catastrophe that changed the biosphere over the course of tens of millions of years. The results of the analysis of carbon and oxygen isotopes from geological layers show sharp changes in ecosystems that manifested over millions of years, indicating that recovery was long and painful. Ultimately, this catastrophe paved the way for a new era in evolution, when new organisms replaced the extinct ones. Scientific data collected over many years confirmed that the Permian extinction was the result of a complex interaction between volcanic activity and climate changes caused by gas emissions, which in turn led to the most significant changes in the history of life on Earth. Mass extinctions are catastrophic events that have a devastating impact on Earth's biosphere, leading to the simultaneous disappearance of numerous species. These events have occurred throughout the planet's history and are often accompanied by significant changes in climate, geological processes, or cosmic phenomena. For example, well-known mass extinctions like the Permian and Cretaceous events are observed at the boundaries of geological periods when the global ecosystem is under severe stress. As a result of such catastrophes, up to 95% of all species on the planet can perish. It is important to note that such events can be caused by various factors, from volcanic activity that releases enormous amounts of carbon dioxide and sulfur into the atmosphere, to meteor impacts, such as the one that occurred around 60 million years ago when an asteroid struck the territory of modern Mexico, creating the Chicxulub crater. This impact caused global changes, including a nuclear winter that destroyed many ecosystems. In Earth's geological history over the past 450 million years, at least 5 major mass extinctions have occurred, each leaving its mark on the diversity of life. In the face of rapid climate change, many organisms are unable to adapt to new conditions, making them vulnerable to extinction. For instance, at the end of the Cretaceous period, changes in ocean temperatures and sea levels significantly worsened conditions for marine life, leading to their mass disappearance. Furthermore, even small changes in ocean currents can have a destructive impact on marine ecosystems, disrupting food chains. As a result, each wave of extinction creates unique conditions for the survival of the remaining organisms, which in turn influences the evolution of life on Earth. This interaction between extinction and adaptation leads to the emergence of new species that can occupy the niches left vacant by the disappearance of previous inhabitants. The tension between biodiversity and the threats posed by planetary changes creates a fragile balance that can be disrupted at any moment. For example, the current climate change caused by human activity is already leading to the mass extinction of species, which is a cause for serious concern among scientists. According to estimates, between 20 and 15% of all species are on the brink of extinction due to climate change and habitat destruction. This process, which scientists refer to as the sixth mass extinction, could become the most significant in human history if immediate action is not taken. The future of Earth's biosphere depends on the ability of ecosystems to adapt to rapidly changing conditions, as well as on human actions, which more than ever before influence the course of the history of living organisms. It is important to remember that life on Earth has been constantly evolving for millions of years, but each new epoch has brought risks and threats, giving rise to new forms of life. Scientific research shows that in the face of global changes, only those species that can adapt to the new environment survive. For example, some plants and animals begin to migrate in search of more favorable conditions, while others may develop resistance to new diseases or stresses. Scientists continue to study these processes to understand how life on Earth can survive in conditions where familiar ecosystems are declining. Therefore, it is important to realize that life on Earth has always been on the brink of extinction, and it has only been able to continue thanks to evolutionary mechanisms. Scientific observations show that significant evolutionary changes often occur during crises, shaping new biodiversity. The Permian extinction, which occurred around 250 million years ago, is considered the most extensive known mass extinction on Earth, during which up to 96% of marine and 70% of terrestrial species disappeared. This period was marked not only by a sharp decrease in biological diversity, but also by a slow decline of life in both oceans and on land, leading to the disappearance of entire groups of organisms and the desertification of once rich ecosystems. At the time when life on the planet was experiencing one of its most critical phases, the world was gripped by global climate changes, volcanic activity, and changes in sea level. In particular, large masses of basaltic lava, known as the Siberian Traps, were formed as a result of volcanic activity and released enormous amounts of carbon dioxide and sulfur into the atmosphere. This led to a greenhouse effect, resulting in a rapid warming of the climate and oxygen depletion in the oceans. Scientific research shows that the temperature of the seawater could have risen by several degrees, creating conditions that were unsuitable for most marine organisms. For example, coral reefs, which were home to many species, began to disappear, and marine ecosystems became less diverse. The diversity of marine organisms decreased, and many species, such as trilobites and brachiopods, were on the brink of extinction. On land, the situation was no better. Forests that were once teeming with life began to wither. Evidence suggests that many plant species were unable to adapt to the changing conditions and began to go extinct. The disappearance of entire groups of organisms, such as moscovites and various amphibians, became one of the most striking examples of this catastrophe. As a result, ecosystems that were once full of life became empty and lifeless. A significant aspect of the Permian extinction is that it led to fundamental changes in ecosystems, which shaped a new face of life on Earth. After this extinction, the Mesozoic era began, which saw the emergence of dinosaurs and other new forms of life. Research shows that the evolutionary changes that occurred after the Permian extinction were so significant that they determined the further trajectory of the development of the biosphere for many millions of years. The Permian extinction became a significant milestone in the history of Earth, demonstrating how ecological catastrophes can radically transform life on the planet and create conditions for the emergence of new species. Scientific research conducted in recent decades continues to reveal details of this event, clarifying the causes and consequences, which helps understand how contemporary life can react to such global changes. There is evidence that this process of extinction lasted not for 1 year, but stretched over millions of years, highlighting its scale. Research has shown that many ecosystems did not recover even after millions of years following this event, raising questions about the resilience of the biosphere to catastrophic changes. After the Permian extinction, which occurred around 250 million years ago, the world underwent profound changes. The planet was left with desolate ecosystems where once thriving organisms had disappeared, leaving behind only emptiness. This extinction wiped out approximately 90% of all marine species and 75% of terrestrial species, making Earth a vast blank canvas ready for a new evolution. Food chains became significantly simplified as the dominance of a few surviving groups limited the diversity of life forms. For instance, in the seas, only a few species like marine reptiles and some crustaceans remained, which managed to adapt to the new conditions. On land, only a few plant groups, such as gymnosperms, survived and began to fill the vacant niches. These groups, in turn, became the foundation for new ecosystems that were just beginning to form. Approximately 1 million years after this event, during the Triassic period, a set of evolution began as the freed-up ecosystems started to fill with new forms of life. The conditions for this were changes in climate and geographical transformations that opened access to new resources. It was during this time that the first dinosaurs began to develop, occupying dominant positions due to their ability to quickly adapt to diverse conditions. In the Triassic period, various groups of reptiles, including the ancestors of modern mammals, began to emerge. This period also saw the active development of insects, which facilitated pollination of plants and the creation of more complex ecosystems. These changes in ecosystems became possible because the surviving species began to evolve, adapting to the new conditions. Research shows that this period became the main starting point for further life development on Earth, leading to the appearance of diverse forms that will exist in the future. The new Triassic world was characterized not only by the dominance of reptiles, but also by the appearance of the first mammals, which later opened the way for the evolution of warm-blooded animals. This process took millions of years, but it became the basis for the formation of the modern ecosystems we know today. The evolutionary paths chosen by the surviving groups formed the biological diversity that became the foundation for future forms of life. For example, in the Triassic period, the first ancestors of lizards and turtles appeared, which began to occupy new ecological niches, leading to the development of new forms of life. After the Permian extinction, the world became a place where competition for resources was renewed with new vigor. And it was during this time that evolution began, which laid the foundation for the dominance of dinosaurs, lasting over 100 million years. Impact events on Earth are collisions with large celestial bodies that instantaneously alter planetary conditions, triggering global catastrophes. These events pose severe tests for ecosystems and the biosphere, capable of wiping out existing life forms and creating new conditions for evolution. For instance, such catastrophes can occur due to collisions with asteroids or comets, which upon entering the atmosphere cause powerful explosions, heating the surrounding environment to thousands of degrees Celsius. This releases energy equivalent to many megatons of TNT, resulting in the formation of giant waves, tsunamis, and even global fires covering vast territories. Chemical reactions resulting from such impacts can lead to the formation of new minerals and changes in the chemical composition of the atmosphere. For example, during a collision, enormous quantities of dust and gas are released, blocking sunlight and causing a sharp drop in temperature, which can lead to long-term climate changes known as nuclear winter. Throughout Earth's history, numerous such events have been recorded, each leaving its mark on the planet's geological and biological record. Impact events create chaos, destroy familiar ecosystems, and cause mass extinctions, as seen when a large meteorite struck 13,000 years ago, leading to the disappearance of many animal species and changes in the landscape. These catastrophes remind us of the fragility of planetary balance in the face of powerful cosmic forces. Earth, constantly moving within our galaxy, is at risk of collisions with objects that can appear from nowhere. For example, in recent decades, scientists have observed celestial bodies approaching our planet, some of which have the potential for significant destruction. According to astronomers, about 100 tons of cosmic debris falls on Earth every hour, ranging from small particles to large asteroids. NASA data from the past century includes significant incidents, such as the Tunguska meteorite fall in 1908, which destroyed a forest area of over 12 square kilometers. Scientific research shows that even small objects can cause serious consequences, including local climate changes, pollution, and species extinction. Considering all these factors, it becomes clear that the planet is in a state of constant risk, and each collision could become a turning point in Earth's history. Ongoing scientific projects to track and study dangerous asteroids continue, but the reality is that we still cannot fully predict or prevent the consequences of such impacts, which can change the face of our planet in a matter of seconds. When a celestial body, such as an asteroid or meteorite, enters Earth's atmosphere, it moves at an enormous speed, reaching several tens of kilometers per second. At this stage, its temperature can reach several thousand degrees Celsius due to friction with atmospheric gases. Upon impact with the planet's surface, a tremendous amount of energy is released, equivalent to the explosion of a nuclear device. For instance, the Chelyabinsk meteorite that fell in 2013 released energy of around 14 kilotons in TNT equivalent, causing significant destruction on the ground and in the air. The shockwave formed by the impact spreads at the speed of sound, causing powerful explosions and destruction over a large distance from the impact site. This process also results in the ejection of molten material and debris into the atmosphere, which can rise to heights of up to 100 kilometers, creating bright light effects visible from afar. The formation of a crater occurs due to the immense pressure and temperature, causing the ground beneath the asteroid to explode and form a crater. Crater rims typically have a characteristic shape with a central uplift, which is formed due to elastic waves rising from the depths of the Earth's crust after the impact. For example, the Tunguska crater, formed in 1908, has a diameter of around 500 meters and a depth of up to 20 meters. Additionally, seismic waves generated by the impact spread across the planet, causing tremors detected by seismographs up to 1,000 kilometers from the impact site. These waves can be powerful enough to trigger earthquakes in coastal and even inland regions. The process of forming an impact crater is a complex physical mechanism that requires the interaction of many factors, including the speed, mass, and angle of descent of the celestial body. The Chicxulub crater is located on the Yucatan Peninsula in Mexico and has a diameter of approximately 100 kilometers. This site witnessed one of the most catastrophic events in Earth's history, which occurred around 65 million years ago. The impact of an asteroid, which led to the formation of the crater, caused a mass extinction, resulting in the disappearance of about 75% of all species on the planet, including dinosaurs. Scientific research using radiometric dating methods has shown that the crater was formed by the collision with an object estimated to be 10 kilometers in diameter. This impact generated powerful seismic waves and ejected a vast amount of dust and gases into the atmosphere, leading to a rapid change in climate. As a result of this event, factors such as acid rain and significant temperature drops emerged, which contributed to the demise of ecosystems and the alteration of biological processes. The crater is buried under a layer of sedimentary rocks, and its structure has been extensively studied by scientists like Dr. Alan Hildebrand, who led an expedition to investigate the crater in 2001 using drilling equipment to extract samples. These samples help to understand the exact nature of the impact and its consequences for the biosphere. The Chicxulub crater is now a UNESCO World Heritage Site, and its study continues. It is interesting to note that the crater was only discovered in the 18th century, when researchers began to identify its geological structure. The location of the crater in the jungles of Yucatan attracts many scientists and tourists eager to see the place where the cosmos directly influenced the evolution of life on Earth. Recent research has also shown that the crater may contain remnants of life that existed before the impact, making it a significant object for paleontologists. The complex ecosystem surrounding the crater includes unique plant and animal species that have adapted to the region's conditions, further highlighting how catastrophes can shape life on the planet. The Chicxulub crater remains a symbol of how extraterrestrial forces can directly intervene in the history of our planet, opening new horizons for understanding evolution and the interaction of various species. The asteroid that collided with Earth and created the Chicxulub crater had a diameter of about 10 kilometers and was one of the most destructive objects ever to impact our planet. The collision occurred approximately 65 million years ago, when an asteroid traveling at around 20 kilometers per second struck the Earth's surface. The energy of the impact was estimated to be equivalent to 10 billion atomic bombs, similar to that dropped on Hiroshima, resulting in a massive release of energy. At the moment of impact, a flash of light brighter than the sun was produced, which could be observed from thousands of kilometers away. The shockwave caused instantaneous vaporization of rocks, leading to the formation of a crater with a diameter of about 180 kilometers. During the formation of the crater, a vast amount of material was ejected into the atmosphere, causing global climate changes. Some of the ejected material reached the stratosphere and even entered space, creating clouds of molten rock and debris that later fell to the Earth's surface as microscopic particles. This catastrophic process, lasting only a few minutes, led to mass extinctions of species, including dinosaurs, and had a significant impact on the ecosystems of the entire planet. The aftermath of the impact included forest fires, acid rain, and darkness caused by dust and smoke filling the atmosphere, altering the familiar conditions of life on Earth. The area around the impact site, now known as the Yucatan Peninsula, still bears the traces of this catastrophic event, making it a center for scientific research into the consequences of the collision. After the impact of the Chicxulub asteroid, which occurred approximately 66 million years ago, the planet experienced a true catastrophe with unpredictable and devastating consequences. At the moment of collision, energy equivalent to billions of atomic bombs was released, causing firestorms that engulfed vast territories. Temperatures in the impact zone reached thousands of degrees Celsius, instantly vaporizing water in rivers and oceans, raising colossal clouds of steam and dust into the atmosphere. This, in turn, led to catastrophic tsunamis, with wave heights exceeding 100 meters, sweeping away everything in their path, including entire ecosystems. Underwater earthquakes, caused by the displacement of the Earth's crust, exacerbated the situation, creating new underwater reefs and rifts that forced ocean water onto land. These destructions disrupted the natural order of life, and many species of animals and plants, which had adapted to their environment over millions of years, found themselves on the brink of extinction. Within a few hours after the impact, the sky was shrouded in dark smoke that blocked out sunlight, creating conditions reminiscent of eternal night. This led to a sharp drop in surface temperature, known as the nuclear winter, which in turn caused acid rain that destroyed vegetation and poisoned freshwater sources. The drop in pH in soil and water bodies made survival impossible for most organisms. Climate change and the destruction of ecosystems led to mass extinction. Nature, which had evolved over millions of years, lost its stability in a matter of hours. Studies show that more than 75% of all species on the planet, including dinosaurs, went extinct as a result of these catastrophic changes. The Chicxulub impact marked the beginning of the end for many living beings, and even the most resilient species could not cope with the aftermath. Scientific data confirm that this period was one of the darkest in Earth's history, when life as we knew it changed completely, and the world we live in today is a result of this destructive cataclysm. The impact of Chicxulub caused what is known as the impact winter, which had catastrophic consequences for the planet's ecosystems. Immediately after the impact, a massive amount of dust was released into the atmosphere, forming clouds that blocked sunlight for many months, if not years. Scientific research shows that the surface temperature of Earth dropped by 10 to 12 degrees Celsius, leading to a sharp cooling of the climate. For instance, according to geologist and paleontologist David Kapell, this sudden drop in temperature caused photosynthesis to virtually cease. Without sunlight, plants could not produce oxygen and nutrients, which disrupted the foundation of food chains. This affected not only terrestrial ecosystems, but also oceans, where plankton, which is at the base of the food chain, also suffered from the lack of light. The mass extinction that followed was one of the largest in Earth's history. Biologists estimate that at the end of the Cretaceous period, up to 95% of all marine species and more than 75% of terrestrial animals went extinct. The extinction of dinosaurs is just the tip of the iceberg, as many other groups, such as ammonites, marine reptiles, and even some mammals, were also affected. As a result, ecosystems that existed before the impact were destroyed, and Earth was plunged into darkness and cold. This climate collapse lasted for at least 10,000 years, forcing surviving species to adapt to completely new conditions. The changes in ecosystems were so significant that they allowed mammals to occupy the niche previously held by dinosaurs. Ultimately, this led to the evolution of modern mammals and even humans. The long-term consequences of the Chicxulub impact made Earth a place where life, as we know it, was fundamentally changed, and ecosystems that once thrived were completely transformed. In the field of paleontology, a notable discovery is the fossils found in deposits related to this catastrophic event, demonstrating how quickly life on Earth could change. For example, fossils of marine creatures found in layers dated to around 66 million years ago show a sharp decrease in biodiversity. The Chicxulub impact, which occurred around 66 million years ago, was a catastrophic event that led to the mass extinction of dinosaurs, which had dominated Earth for over 150 million years. As a result of the collision of a massive asteroid estimated to be 60 kilometers in diameter, with Earth in the vicinity of the modern Yucatan Peninsula in Mexico, catastrophic changes occurred in the climate and ecosystems. The impact caused powerful explosions that released energy equivalent to billions of atomic bombs, leading to the creation of extensive forest fires, dust and gas emissions into the atmosphere. This change was so abrupt that ecosystems far from the impact site, including tropical forests and marine ecosystems, suffered from its consequences. Temperatures on the Earth's surface dropped and then rose sharply, causing acid rain and changes in the atmosphere making it less suitable for life. Dinosaurs, which dominated the planet, were unable to adapt to these conditions. For example, large herbivorous dinosaurs such as Tyrannosaurus and Triceratops were unable to find enough food because the vegetation changed and decreased. Small predators like velociraptors also suffered from resource shortages. Research by paleontologists shows that the survival of dinosaurs depended on their ability to adapt to new conditions. But most of them, including such magnificent creatures as Brachiosaurus and Stegosaurus, were unable to cope with the sudden changes in their habitat. As a result, by the end of the Cretaceous period, at the boundary with the Paleogene, almost all dinosaur species had disappeared. This extinction opened the door for new forms of life, such as mammals and birds, which were able to occupy the niches previously occupied by dinosaurs. It is important to note that this event was a turning point in the history of life on Earth, altering the course of evolution. Leading paleontologists such as Din K. Quinn emphasized that this period marked not only the end of the dinosaur era, but also the beginning of a new epoch in which mammals began to dominate the planet. Known fossil finds show that in the following millions of years after the impact, new species of animals began to appear on Earth, which were able to survive in the conditions created by the Chicxulub impact. After the mass extinction that occurred approximately 66 million years ago, only a few species survived and adapted to the new conditions. Small mammals, such as primitive rodents and insectivores, found themselves in a favorable position due to their small size and high fertility. For example, the research of paleontologist David Elliott confirms that small mammals, such as the genera Purgatorius and Didelphodon, began to actively reproduce and fill the ecological niches left vacant by the disappearance of dinosaurs. Their ability to be active at night helped them avoid predators and allowed them to utilize resources that were inaccessible to larger animals. Birds that survived, such as Archaeopteryx, used their wings to quickly move between trees, which gave them an advantage in finding food and shelter. Their feathers and ability to fly facilitated their spread to new territories, which in turn led to the diversification of species. Crocodiles, as research shows, adapted to aquatic environments, allowing them to use bodies of water as shelter from drought and as a source of food. Their cold-bloodedness ensured energy conservation, which was critically important in conditions where access to food was limited. Turtles, in turn, developed a hard shell that protected them from predators and allowed them to survive in harsh conditions such as drought or food scarcity. As a result of these adaptations, these groups of animals began to actively evolve and fill free ecological niches. Over the next millions of years, according to paleontological findings, these species began to develop new forms and sizes, leading to the appearance of modern representatives of these groups. For example, by the beginning of the Eocene, which started around 55 million years ago, mammals already constituted a significant part of the ecosystem, including the first ancestors of modern elephants and primates. Birds, in turn, began to develop a diversity of forms and sizes, allowing them to occupy numerous ecological niches, from predators to herbivores. This process of species radiation became fundamental in shaping the modern ecosystems and ecological interactions that we observe today. By the beginning of the Miocene, approximately 18 million years ago, new species of mammals emerged, including the ancestors of modern predators and herbivores, which was a testament to the successful adaptation and evolution of these groups of animals in conditions that were vastly different from those that existed before the extinction. Supervolcanoes are colossal geological structures that differ from ordinary volcanoes in the scale of their eruptions and their potential impact on the planet. These giants can eject hundreds and sometimes thousands of cubic kilometers of volcanic material in a single eruption. For comparison, a typical volcano can eject from 1 to several cubic kilometers. Supervolcanoes form as a result of the accumulation of magma beneath the Earth's crust, leading to the formation of enormous chambers capable of holding vast amounts of molten rock. When pressure reaches a critical level, a catastrophic eruption occurs, which can result in the formation of a caldera, a vast depression formed by the collapse of the volcano's upper part following an eruption. One of the most well-known processes associated with supervolcanoes is the release of pyroclastic flows, which can travel at speeds exceeding 300 kilometers per hour and destroy everything in their path. Eruptions from supervolcanoes can significantly impact global climate, causing abrupt temperature changes on the planet. For example, the release of ash and gases into the atmosphere can block sunlight, leading to a temporary cooling known as a volcanic winter. This phenomenon can last from several months to several years, threatening agriculture and ecosystems over large areas. Studies show that even small-scale eruptions from supervolcanoes can affect the level of carbon dioxide in the atmosphere, potentially leading to long-term climate consequences. Scientists also note that supervolcanoes can be active for millions of years, with their eruption cycles ranging from thousands to millions of years. It is important to note that the diversity of supervolcanoes on the planet is not limited to one region. They can be found both on land and underwater, making their study even more complex. For instance, supervolcanoes can be located near the boundaries of tectonic plates, where plates converge or diverge, creating conditions for their formation. The ability of supervolcanoes to cause global catastrophes and their long-term impact on climate makes them objects of intense scientific interest. Researchers are focused on analyzing volcanic activity, studying geological formations, and monitoring the gases released by supervolcanoes. Understanding these processes is crucial for predicting potential threats to humanity. Supervolcanoes can not only cause climate catastrophes, but also significantly alter ecosystems and influence the migration and survival of various animal and plant species. For example, after a large eruption, mass extinctions can occur, leading to changes in food chains and ecosystems. Studies show that even small climate changes can have a serious impact on agriculture and food security in various regions of the world. Supervolcanoes, therefore, represent powerful geological forces that continue to generate interest and concern among scientists and the public. It is expected that further research in this area will help better understand the dynamics of supervolcanoes and their potential consequences for Earth. Supervolcanoes can eject from 100 to 1,000 cubic kilometers of material in a single eruption. Yellowstone caldera is one of the most impressive geological formations on the planet. With a diameter of approximately 30 kilometers, it is one of the largest in the world. This massive depression was formed as a result of eruptions that occurred about 600,000 years ago, which created a giant magma reservoir beneath the surface. The structure of the caldera includes numerous thermal springs, geysers, and hot springs, such as the famous Old Faithful geyser, which can shoot a column of water up to 45 meters high. These natural phenomena may seem harmless, but they only mask the hidden power that lies beneath the park's picturesque landscapes. Volcanic activity in this area continues, with scientists recording small earthquakes that indicate magma movement beneath the surface. The U.S. Geological Survey's monitoring system tracks changes in temperature and gas emissions, confirming the ongoing activity of the caldera. For example, in 2020, scientists observed an increase in temperature in some hot springs, which may indicate growing volcanic activity. This creates a sense that beneath the shimmering lakes and scenic valleys lies a giant time bomb. Located at the intersection of several tectonic plates, Yellowstone caldera serves as a reminder of how dormant natural forces can suddenly awaken and reshape the landscape in just a few hours. 80% of the park is covered by thermal features, making it a unique place for studying and observing volcanic activity. Geysers, hot springs, and even mud pots, such as the mud pot on the southeast side of the caldera, are just the tip of the iceberg. Beneath them lie extensive underground magma reservoirs capable of causing catastrophic eruptions. Scientific research shows that if Yellowstone caldera were to erupt today, the consequences could be catastrophic not only for the region, but for the entire world. The volcano could release millions of tons of ash and gas into the atmosphere, leading to global climate change and widespread destruction. Scientific data indicates that the last 3 major eruptions occurred approximately every 600,000 years, so the time until the next similar event could be relatively close. This awareness makes us consider how fragile our lives can be beneath the surface, where forces capable of changing the world in an instant lie dormant. The depth of the magma beneath the caldera reaches about 10 kilometers, and its temperature can exceed 1,000 degrees Celsius. Each eruption leaves its mark on geological history, forming unique landscapes and ecosystems that we can observe today. The place where geysers and hot springs are just a small part of a majestic scene underscores the power and beauty of nature, which hides something greater than just scenic views. The last major eruption of Yellowstone occurred around 625,000 years ago and was a catastrophic event that drastically altered the ecosystems and climate of North America. This eruption released approximately 1,000 cubic kilometers of volcanic material, including ash, lava, and gases. Ash that rose into the sky spread over distances of more than 1,000 kilometers, settling over an area stretching from the current states of Montana and Wyoming to Minnesota and Nebraska. As a result, vegetation over large areas was destroyed, and ecosystems underwent significant changes. The sky remained covered in ash for several months, with sunlight barely penetrating the clouds of volcanic material, which significantly lowered the surface temperature, creating a volcanic winter effect. This phenomenon led to a sharp drop in temperature by several degrees Celsius. As a result of this temperature drop, many plant species were unable to survive, which in turn affected food chains and led to mass animal die-offs. Research has shown that such climate changes could persist for several years, preventing many ecosystems from returning to their normal state. Scientists like Dr. Stephen Ronald from the University of Colorado note that such eruptions are a significant factor influencing long-term climate changes observed throughout Earth's history. Volcanic gases, including sulfur dioxide, released during the eruption, created acidic rain, further worsening living conditions over large areas. Complex climate conditions also facilitated the migration of animals seeking more favorable habitats. As a result of these processes, ecosystems that had developed over millions of years were destroyed, and new species began to fill the vacant niches. This catastrophic process resembled a giant mechanism where each detail played its role in creating a new world, marked by the stamp of a volcanic catastrophe. Scientific research shows that the consequences of this eruption were not limited to the local level, but also affected the climate conditions of the entire planet. Some climate change models indicate that the Earth's temperature could have dropped by several degrees over several years following the eruption. Local rivers and lakes filled with volcanic ash lost their clarity, and ecosystems dependent on them began to decline. Research conducted in 2000 by a group of scientists led by Dr. Patrick Griffin showed that the aftermath of this eruption significantly altered the composition of species inhabiting those regions. Scientific data indicates that many species that existed before the eruption disappeared, and new species adapted to the changed conditions took their place. For millions of years, Yellowstone remained a dormant giant, and at any moment it could awaken, reminding us of its power and destructive force. The supervolcano Toba is located on the island of Sumatra in Indonesia and is considered one of the largest volcanoes in the world. Its caldera has a diameter of approximately 130 kilometers and a depth of about 18 kilometers. This eruption, which occurred approximately 74,000 years ago, is one of the most powerful in Earth's history. It led to the release of a vast amount of ash and gases into the atmosphere, causing a global cooling that lasted for several thousand years, known as the volcanic winter. The caldera of Toba was filled with water and formed the beautiful Lake Toba, which is now the largest lake in Southeast Asia. The lake covers an area of about 1,600 square kilometers, with a maximum depth of 540 meters. The serene landscape of the lake, with its crystal-clear water and surrounding mountains, creates an impression of tranquility that contrasts with the potential destructive power hidden beneath its waters. Despite its beauty, scientists warn about the possible activity of the supervolcano. Over the past few thousand years, Toba has shown signs of activity, including small eruptions, such as the one that occurred around 1898, when there was an increase in temperature and activity of underwater sources. These events indicate that the volcanic system continues to function, and beneath the surface, there are vast volumes of magma ready to move. Lake Toba and its surroundings attract many tourists, but scientists strongly advise being cautious about the geological activity in the region. From a historical perspective, the eruption of Toba could have played a crucial role in human evolution, as the cooling could have led to a decrease in the population of Homo sapiens. Scientific research shows that this event could have been catastrophic for ancient populations, pushing them to the brink of extinction. Volcanic rocks found around the caldera contain information about climate changes and human migrations, making Toba an important object of study not only for geology, but also for anthropology. Currently, scientists continue to conduct research to better understand the mechanisms behind supervolcano eruptions and their potential consequences for the planet. The volcanic activity of Toba still causes interest and concern, as a strong eruption could pose a threat to millions of people living in close proximity to this giant. Approximately 74,000 years ago, the most powerful eruption of the Toba volcano occurred, which became a planetary-scale catastrophe. This eruption released about 3,000 cubic kilometers of volcanic ash and gases into the atmosphere, leading to a significant change in Earth's climate. As a result of this release, the sky darkened for many years, severely disrupting the process of photosynthesis and affecting the entire planetary ecosystem. The temperature on Earth dropped by 10 degrees Celsius and remained below the normal level for at least 10 years. Scientists suggest that such a sudden change in climate could have led to a significant reduction in human population, which was already experiencing challenging living conditions at the time. Estimates suggest that the population of ancient Homo sapiens could have been reduced to a few thousand individuals, putting the survival of the species at risk. At that time, people lived in small groups, making them vulnerable to natural disasters and food shortages. Remains found in various regions, such as southern Asia and Africa, indicate that survival became a real challenge for humanity, with interactions between small communities being limited. Additionally, the volcanic winter led to a significant change in migration patterns. Many groups of people began to move to southern regions where conditions were more favorable. This eruption not only changed the climate, but also affected the genetic diversity of humans, as evidenced by studies of modern population DNA. For example, genetic data show that many modern people have common ancestors who survived this catastrophic period, which supports the theory of a bottleneck, a sudden reduction in population size. The eruption of Toba left behind many questions and mysteries about how people were able to adapt to new conditions and continue their existence in such extreme circumstances. This event became a significant milestone in human history, highlighting the vulnerability of our species to the forces of nature. Research indicates that such a powerful eruption, like that of Toba, could occur again, and this warning in the context of current climate changes raises serious concerns among scientists. Volcanic activity is directly linked to climate changes, as eruptions release a massive amount of gases and aerosols into the atmosphere. One of the key components of these emissions is sulfur dioxide and carbon dioxide. Sulfur dioxide, upon entering the atmosphere, condenses into sulfuric acid, forming aerosols that can reflect solar radiation, leading to a decrease in surface temperature. For instance, a study conducted in 2005 by a group of scientists led by Dr. Andrew Engler found that an increase in sulfur aerosol concentrations can lower global temperature by several degrees over a few months following an eruption. At the same time, carbon dioxide, released as a result of volcanic activity, is a potent greenhouse gas. It traps heat in the atmosphere, contributing to global warming. While volcanoes contribute only a small fraction of the total amount of carbon dioxide in the atmosphere compared to human activities, their short-term impact can be significant. For example, in the 20th century, volcanic activity, including eruptions of volcanoes like St. Helens and Pinatubo, led to noticeable changes in climate, as confirmed by numerous climate models. The complex interplay between Earth's internal processes and the climate system is also evident in how volcanic eruptions can affect precipitation. Aerosols formed after eruptions can alter precipitation patterns, causing both droughts and floods in different regions. For instance, research conducted in 2010 showed that volcanic eruptions can change the direction of monsoons, which in turn affects agriculture and water supply. Therefore, volcanic activity creates complex climate effects that can range from short-term temperature changes to long-term changes in precipitation and climate patterns. These processes highlight how internal forces of the Earth, such as plate tectonics and magmatic processes, can directly influence surface climate conditions. In this context, it is important to remember that volcanic eruptions are not the sole factor in climate change, but they are a significant element in the complex system of interactions where multiple factors influence each other. Volcanic activity can cause both abrupt cooling and long-term trends towards warming, depending on the conditions and composition of the emissions. Scientific research shows that understanding these interactions is critically important for predicting climate changes and developing strategies to mitigate them. As a result, studying volcanic activity and its impact on climate becomes necessary in the face of contemporary challenges related to climate change and the increase in frequency of extreme weather events. For example, according to data from the World Meteorological Organization, future climate models should consider possible scenarios of volcanic activity for more accurate predictions of changes. In the year 1818, following the catastrophic eruption of the Tambora volcano in 1816, the world faced an unprecedented natural disaster known as the Year Without a Summer. This eruption, which occurred in Indonesia, released a massive amount of volcanic gases and ash into the atmosphere, leading to a significant decrease in global temperature. In Europe and North America, the summer of 1816 became a true test for both people and nature. Snow fell in June, and temperatures in July dropped to 5 degrees Celsius, which was completely atypical for that time of year. Farmers, expecting a bountiful harvest, were shocked to find frozen crops and gloomy skies instead of blooming fields. In regions such as New York and Connecticut, farmers witnessed their crops, including wheat and potatoes, perish from frost, leading to a sharp decline in food supplies. European farmers desperately sought ways to save their crops, but the strange weather conditions left them no hope. In Switzerland, agronomists noted that instead of the usual summer rains, cold showers came, creating an atmosphere of anxiety and despair. In some places, temperatures dropped so low that rivers froze, and snow could be seen on fields even in midsummer. This anomaly caused widespread unrest among the population, and many people began to seek explanations for the suffering that had befallen them. As a result, food riots broke out, and public discontent grew, leading to increased social tension. In particular, in the United States, mass migrations were observed as people, unable to feed their families, left their lands in search of a better life. In Europe, especially in Germany and France, hunger forced people to gather wild plants and seek alternative food sources. The economic situation worsened, and grain prices skyrocketed. In some countries, such as Ireland, this year marked the beginning of long suffering that later resulted in massive migrations. While some sought ways to survive, others plunged into panic, believing it to be a sign of divine wrath. Scientific explanations were still in their infancy, and people could not understand what had caused these catastrophic climate changes. This summer became a symbol of nature's unpredictability, when familiar cycles were disrupted and human life was threatened. As a result, the Year Without a Summer not only became one of the coldest years in history, but also served as a catalyst for social changes, forcing people to re-evaluate their views on nature and its influence on human life. In this context, the number of victims from hunger and disease increased, and many researchers assert that it was during this year that a new wave of migrations and social changes began, which later shaped the development of entire countries. As a result of the horrors caused by the Year Without a Summer, European cultural life underwent significant changes. During this time, in the 18th century in Switzerland, Mary Shelley, inspired by the gloomy atmosphere and pervasive sense of unease, wrote her famous novel Frankenstein, which was published in 1818. In this work, she explores themes of nature, human existence, and the consequences of scientific progress, creating a monster that became a symbol of fear about what might happen when humans attempt to play the role of God. The inspiration for Frankenstein came from deep reflections on the consequences of climate change and human greed, which reflected the social and cultural sentiments of the time. One of the prominent figures of the artistic movement that emerged in response to these events was the British painter John Constable. His landscapes, such as View of Hayley and Misty Morning Landscape, conveyed gloomy and oppressive moods, reflecting the changes in nature that he observed. In 1707, he created the painting Evening Landscape, which depicts dark clouds looming over rural scenery, symbolizing not only physical climate changes, but also the inner turmoil of people. His works became a projection of the fears and anxieties that gripped society, serving as a reminder of how nature can affect human emotions and creative expression. At the same time, on the continent, artists like Caspar David Friedrich began creating paintings filled with dark and apocalyptic moods. His famous work, The Wanderer Above the Sea of Fog, painted in 1805, visualizes the loneliness and despair that a person feels in the face of nature. Friedrich used dark tones and deep contrasts to convey a sense of loss and fear of the unknown. These paintings became symbols of the era, reflecting the internal conflict of humans and their place in the world, where nature ceased to be a source of inspiration and became an object of fear. In literature of the time, a shift towards dark themes and pessimistic moods was also observed. For example, Lord Byron's poem Childe Harold describes the travels of a hero who encounters destruction and sorrow caused by changes in nature and society. In the works of Byron and his contemporaries, one can see how The Year Without a Summer served as a catalyst for deep reflections on human existence, the nature and the consequences of industrialization. Thus, the cultural impact of The Year Without a Summer manifested in the creation of works that became classics. The novel Frankenstein, the paintings of Constable and Friedrich, and the poetry of Byron, all these creations became an integral part of European cultural identity. Artists and writers of the time transferred their fears and doubts into their works, creating pieces that continue to stir and inspire subsequent generations. These works not only reflect the anxious moods of their time, but also serve as a reminder of how natural disasters can shape human creativity and thought. In 1818, when Frankenstein was published, society began to recognize the consequences of its actions, and this theme remains relevant today. Glacial periods are natural cycles during which large masses of ice and snow cover extensive continental territories. These processes occur over millions of years, and their impact on the planet is difficult to overestimate. During glacial periods, glaciers slowly but inexorably move towards the equator, creating powerful layers of ice that can reach several kilometers in thickness. Approximately every 100,000 years, according to paleoclimatology data, glaciers advance and then retreat, leaving behind a transformed landscape. This cycle of glacier advance and retreat is significantly influenced by changes in Earth's orbital parameters, which affect the solar radiation reaching the planet's surface. Glaciers possess incredible power, capable of shaping the landscape. They carve valleys, create fjords and lakes, alter river courses, and even form new ecosystems. For example, when a glacier retreats, it leaves behind small stones and gravel known as moraines, which serve as evidence of its former presence. Some of these formations can be enormous and represent true mountain systems. As a result of this process, landscape features such as lakes, which often have characteristic U-shaped forms, are created, indicating that a glacier once occupied that location. The impact of glaciers on river systems is also significant. Water released from its frozen state creates new flows that can change the direction and width of rivers. For instance, after the end of a glacial period, the Mississippi River acquired its modern shape due to the melting of glacial waters, which led to the reorganization and expansion of the river system. Scientific research shows that glacial rivers are often more powerful and fuller than their predecessors, resulting in changes to ecosystems and water. The process of glacier formation has continued throughout Earth's history, and they continue to influence climate and ecosystems even today. Currently, there are remaining glaciers on the planet that are continuing to melt, causing concern among scientists. These changes can lead to sea level rise and climate change, which in turn will affect millions of people living in coastal areas. Glacial periods are not just part of distant history. They are an essential part of the current ecosystem and climate changes. Scientists like Dr. Clayton M. Bennett from the University of California are studying these processes by analyzing ice samples and moraine deposits to understand how climate change affects the current state of glaciers. These studies show that glacier coverage is significantly dependent on temperature changes, leading to a cycle of freezing and thawing that has continued for thousands of years. Examples of this include glaciers in Greenland and Antarctica, where there has been a sharp decrease in glacier area over the past few decades, confirming that glacial cycles continue to influence our planet. Glacial periods represent not only historical records, but also a living scientific problem that humanity is facing today. Research shows that due to global warming, the temperature on Earth is rising, leading to accelerated glacier melting. 80% of glaciers in the Alps have already lost a significant portion of their mass over the past 50 years. Undeniable facts show that glaciers that were once considered eternal are now under threat of disappearance, which in turn threatens ecosystems and humanity. The last ice age occurred around 20,000 years ago, when a significant portion of the northern hemisphere was covered by a thick layer of ice, reaching up to 3 kilometers in some places. This glaciation, known as the Worm glaciation in Europe, and the Wisconsin glaciation in North America dramatically altered climate conditions and lowered global sea levels by more than 100 meters. Today, we can imagine a world where vast territories, from Scandinavia to Canada, were covered by ice sheets stretching thousands of kilometers inland. Before the advancing ice front, cold tundras and steppes emerged, populated by unique flora and fauna of the Ice Age, including mammoths, woolly rhinos, and giant reindeer. These animals adapted to the harsh conditions by developing thick fur and specific behavioral traits that allowed them to survive in the constant cold. For example, mammoths, reaching heights of up to 4 meters, had a thick layer of fat under their skin and long tusks that they used to dig through snow in search of vegetation. During this time, climate zones underwent significant changes. Arctic conditions spread to areas that are now temperate. Forests retreated southward, giving way to vast ice plains and tundras. Survival became an art form, and human communities, such as hunter-gatherers, adapted by creating specialized tools for hunting large animals and gathering berries and roots to sustain their existence. Research indicates that people began migrating southward as the climate began to warm and the ice retreated, opening new lands for settlement. According to data collected by an international team of geologists, during this period, a unique ecosystem known as megafauna existed on the territories of modern-day United States and Canada. This ecosystem was characterized by the coexistence of giant herbivores and predators, such as saber-toothed tigers and giant bears. This ecosystem was unstable and dependent on climate changes. As temperatures began to rise, many species went extinct without adapting to the new conditions. At the same time, sea levels began to rise, and continents began to take on their modern outlines, flooding coastal areas and creating new marine ecosystems. Thus, the last ice age was not just a period in Earth's history, but a complex and dynamic process involving climate, fauna, and human communities. Glaciation shaped the landscape we know today and left traces that archaeologists and geologists continue to study. Modern research on glacial deposits and marine sediments helps us better understand how past climate changes influenced the development of civilization and ecosystems. For example, ice cores extracted from Greenland show that temperatures fluctuated during this period, which could have influenced the migration routes of animals and humans. Research indicates that the climate changes that occurred during this period were the primary factor determining how ecosystems evolved and changed over thousands of years. The megafauna of the last ice age, which lasted around 100,000 years and ended approximately 12,000 years ago, was truly impressive. Mammoths, reaching heights of over 4 meters at the shoulder, had fur up to half a meter long, which allowed them to survive in cold conditions. These giant herbivores, belonging to the elephant family, inhabited tundra and steppe zones, where they grazed on grassy plains, leaving their powerful footprints on frozen ground. Woolly rhinos, another colossus of the Ice Age, were covered in thick fur and had distinctive curved horns, which they used for protection against predators and for fighting with other males. They could reach lengths of 3 meters and weigh between 1 and 3 tons, making them some of the largest mammals of the time. Cave bears, which went extinct around 30,000 years ago, were not only larger than modern bears, but were also omnivorous predators that used their powerful jaws to tear meat and roots. They could weigh up to a ton and reach lengths of over 3 meters, making them formidable opponents in the struggle for food. Saber-toothed cats, also known as smilodons, had unique teeth that could reach up to 20 centimeters in length. These predators used their sharp fangs to attack large prey such as mammoths and rhinos. Their adaptations for hunting included powerful hind legs and high speed, allowing them to sneak up on prey and make sudden attacks. Megafauna played a key role in the ecosystems of the time, maintaining a balance between herbivores and carnivores. Mammoths and rhinos, by eating grass and shrubs, helped spread seeds and maintain open landscapes, allowing other species to survive. Cave bears, as carnivores, controlled the population of herbivores, keeping the ecosystem stable. Saber-toothed cats, through their hunting strategies, provided the necessary amount of food for other predators such as wolves and large mammals. These complex interactions between species created a dynamic but fragile ecosystem, where each element played a unique role. As the climate changed and the last ice age began, megafauna faced new challenges such as reduced habitats and competition for resources. Around 12,000 years ago, as the ice sheets retreated, megafauna began to go extinct, a result of both climate change and human hunting, as people began to actively settle new territories. By the end of the last ice age, many of these magnificent creatures disappeared, leaving behind only fossil remains and stories that continue to captivate scientists and nature enthusiasts around the world. For example, in the 20th century in Siberia, nearly whole mammoths were found preserved in permafrost, providing researchers with insights into the diet and lifestyle of these animals. The melting of glaciers at the end of the Pleistocene epoch led to significant changes on the planet, freeing up vast territories from multi-kilometer ice cover. This phenomenon began approximately 14,000 years ago, when temperatures began to gradually rise as a result of natural climatic cycles. As a result, large areas previously occupied by glaciers became accessible to new ecosystems. The formation of lakes and new river systems became an integral part of this process. As the ice retreated, depressions formed and filled with meltwater, creating large bodies of water such as Lake Michigan and Lake Huron in North America. The global sea level gradually rose, increasing by more than 100 meters due to the melting of glaciers in Greenland and Antarctica, which significantly altered coastal lines and ecosystems in coastal regions. In the places where the glaciers had retreated, new ecosystems began to form. Forests, gradually advancing northwards, replaced tundra and taiga. For example, in the area of modern Canada and Alaska, around 12,000 years ago, coniferous forests began to appear, providing habitats for numerous animal species such as mammoths and bison. Research shows that between 10 and 8,000 years ago, forests reached their maximum extent, contributing to increased biodiversity in these regions. These changes also affected animal migration routes, which followed the changes in vegetation. Research conducted by scientists from the University of California shows that new ecosystems provided conditions for the growth of populations of species such as moose and deer, which found refuge in warmer conditions. Additionally, as forests advanced northwards, there was a replacement of species. Coniferous trees such as spruce and pine displaced more cold, hardy plant communities. Around 7,000 years ago, in some regions of Europe, the formation of mixed forests began, which also contributed to the appearance of new animal and plant species. In place of cold and harsh conditions, milder ones emerged, facilitating the development of agriculture and a settled way of life for humans. These changes led to the formation of a farming culture, especially in regions such as Mesopotamia, where conditions became favorable for the production of grain. With each decade, this melting opened up new possibilities for life on Earth, creating conditions for the formation of modern ecosystems and civilizations. During this time, the global sea level rose by more than 100 meters, leading to the flooding of extensive coastal territories and changes in climatic conditions in various parts of the world. During the melting of glaciers, catastrophic floods occurred that drastically altered the landscape. One example is the breach of glacial lakes, which could cause massive flows of water that swept everything in their path. Such events occurred when glacial lakes formed by the melting of ice overflowed, and water broke through natural dams created by gravel and silt deposits left by glaciers. As a result, for instance, in the area of Lake Missouri, which was located in the territory of the current state of Montana in the USA, powerful flows were formed that caused megafloods. Over the course of several days or even hours, water eroded rocks, forming new valleys and canyons, such as the Grand Canyon. The force of these floods was so great that they moved huge blocks of stone weighing thousands of tons, leaving behind traces of destruction. From time to time, the power of these floods led to the formation of a specific relief known as scabland, where numerous landslides and rockfalls created complex structures on the surface of the Earth. Such processes occurred, for example, in the Rocky Mountains, where breaches of glacial lakes formed complex networks of canyons and gorges that later attracted the attention of geologists. During the last glacial maximum, which occurred approximately 20,000 years ago, many glacial lakes were in a state of readiness to break through. And when this happened, the scale of destruction was enormous. Scientific research shows that the force of water could reach speeds of up to 100 kilometers per hour, allowing it to erode rocks and form landscapes that we can observe today. For example, in the area of Lake Superior, breaches of glacial lakes led to the formation of deep canyons known as glacial canyons. These events demonstrate how quickly and dramatically nature can change the face of the planet, leaving behind deep traces in the form of new geomorphological features. As a result of these catastrophic floods in North America, river systems were formed that continue to be important water arteries for ecosystems. These events not only shaped the landscape, but also influenced the climate conditions in the region, altering the distribution of precipitation and temperatures. Breaches of glacial lakes also contributed to the creation of new ecosystems that emerged on the sites of previously flooded territories. These floods left behind not only physical changes, but also altered the biological diversity, as new conditions gave rise to new species of plants and animals. At the end of the Pleistocene epoch, approximately 15,000 years ago, Earth experienced a mass extinction of megafauna, which affected numerous large mammals such as mammoths, mastodons, and giant ground sloths. This extinction was the result of a combination of climate changes and human pressure, leading to the disappearance of an entire complex of species that formed unique ecosystems of the Ice Age. For example, mammoths inhabited vast territories from North America to Europe and Asia, with populations numbering in the hundreds of thousands. It has been established that the last mammoths went extinct around 4,000 years ago on the isolated island of Wrangel in the Arctic Ocean. Their extinction was not only due to climate changes that reduced their habitat range, but also to human hunting, which used their bones and meat for various purposes. Mastodons, which were similar to mammoths but had shorter and more direct tusks, went extinct in North America around the end of the last Ice Age maximum. These creatures lived in forest ecosystems and fed on tree leaves. The reduction in forest area and changes in climatic conditions that affected food availability also played a role in their extinction. Giant ground sloths, which lived mainly in North and South America, were true giants of their time, reaching heights of over 4 meters. They went extinct around 10,000 years ago, and as with other species, the main factors were climate change and hunting. Additionally, many other large mammals, such as the shaggy rhinoceros and the giant horse, also disappeared during this period. Research shows that changes in temperature and vegetation, combined with human impact, such as hunting and landscape alteration, led to catastrophic consequences for megafauna. One of the reasons why megafauna could not adapt to rapidly changing conditions was their slow reproduction. For example, mammoths reached sexual maturity only at 5 years old, and pregnancy lasted almost 2 years. This meant that in the face of rapidly changing climates and increased hunting, their populations could not recover. While megafauna was disappearing, small mammals and birds began to dominate, which in turn altered the ecosystems and their structure. To study these processes, scientists use dating methods such as radiocarbon dating to determine the time of extinction of various species. For example, the analysis of bones and teeth shows that the extinction of megafauna occurred over several thousand years, not instantaneously. Overall, the extinction of megafauna at the end of the Pleistocene was one of the most significant events in Earth's history, having a profound impact on ecosystems and biological diversity on the planet. Meteorite craters are clear evidence of Earth's interaction with the cosmos, left behind as a result of collisions with asteroids and comets. These craters are not just geological formations, but genuine windows into the history of our planet, preserving traces of catastrophic events that have occurred over millions of years. There are several types of craters, including simple and complex ones, which form depending on the size and speed of the impact. For example, a collision with a meteorite just a few dozen meters in diameter can create a crater up to 1 kilometer in diameter. Meanwhile, larger objects like asteroids can leave traces spanning tens or even hundreds of kilometers. Meteorite craters are actively studied by scientists, and their analysis helps understand the impact of cosmic impacts on Earth's climate and ecosystems. For instance, it is believed that the fall of a giant meteorite on the territory of modern-day Yucatan around 65 million years ago was one of the causes of the mass extinction of dinosaurs. This event disrupted most ecosystems and led to a sharp change in climate, which is confirmed by geological layers containing high concentrations of iridium, a rare element characteristic of meteorites. These traces in Earth's geological record show that our planet is not an isolated system, but is constantly subjected to the influence of external cosmic forces. According to estimates, Earth encounters tens of thousands of meteorites each year, but most of them burn up in the atmosphere, leaving only small fragments that can reach the surface. However, even small meteorites entering the atmosphere can cause powerful explosions, as happened in Siberia in 1908, when a meteorite exploded over the taiga, destroying forest over an area of more than 2,000 square kilometers. These events serve as a reminder of how vulnerable Earth is to the powerful forces of the cosmos, capable of changing the familiar conditions of life at any moment. Astronomers and planetary scientists continue to monitor large objects that may pose a threat to our planet, developing methods for tracking and assessing the potential risk. Each discovered meteorite and each found crater adds a new page to the history of Earth, confirming that interaction with the cosmos is not a rarity, but a constant part of life on our planet. In general, meteorite craters are not only geological artifacts, but also keys to understanding broader processes occurring in the solar system. The Arizona crater, also known as Meteor Crater, is one of the most impressive geological formations on Earth. It was formed by the impact of a meteorite, estimated to have been around 30 meters wide and weighing approximately 250,000 tons. This event occurred about 50,000 years ago, which, in comparison to the age of the Earth, is relatively recent. The crater has a diameter of about 1 kilometer and a depth of more than 200 meters, making it one of the largest meteorite craters in the world. Visually, the crater is breathtaking. Its edges drop into a chasm, and its floor is strewn with debris and sand, giving the impression of looking at a giant wound on the planet's surface. Standing at the edge of the crater, one feels the power and scale of the event that occurred here when the meteorite struck the Earth at an incredible speed, exceeding 20 kilometers per second. During the impact, so much energy was released that it was equivalent to the explosion of dozens of atomic bombs. The preserved structure of the crater has remarkably well survived the centuries. Erosion and other geological processes have not significantly altered its shape, allowing scientists and tourists to observe it in its nearly original form. Viewing platforms have been set up at the edge of the crater, offering a stunning view of this natural wonder. On a clear day, one can see how the sunlight plays on its walls, highlighting their relief and texture. The crater is also a subject of scientific research. Geologists and astronomers study it to better understand how meteorites affect our planet. Data on the composition of the soil and minerals found in the crater help recreate the picture of the meteorite's fall and its consequences for the Earth. The study of Meteor Crater contributes to a deeper understanding of processes that occur on other planets, such as Mars and the Moon, where traces of meteorite impacts are also found. For example, scientists study craters on the Moon to compare them with the Arizona crater and draw conclusions about the geological activity on these celestial bodies. The Arizona crater is not only an important object for scientific research, but also attracts thousands of tourists each year who want to see this unique formation with their own eyes. The Popigai crater, located in Siberia, is one of the largest impact craters on Earth, with a diameter of approximately 120 kilometers. This colossal depression formed around 46 million years ago as a result of a collision between Earth and an asteroid about 30 kilometers in diameter. Unlike more well-known craters such as Chicxulub in Mexico, the Popigai crater remains relatively inaccessible, situated in remote and harsh terrain where severe climate and permafrost create unique conditions. The crater is surrounded by high mountain ranges and is itself overgrown with forest and taiga, making it difficult to study. The uniqueness of this place lies not only in its size, but also in the fact that rare impact diamonds were found here, formed due to the high temperatures and pressures generated by the impact. These diamonds have a unique crystal structure and differ from the traditional diamonds mined in mines. For example, in 2001, a group of scientists led by Professor Igor Grigoriev from the Institute of Geochemistry and Analytical Chemistry of the RAS discovered crystals up to 1 millimeter in size in the crater, containing traces of rare earth elements such as hafnium and niobium. These findings indicate that the conditions under which the diamonds formed were unique and do not occur in ordinary geological processes. Research shows that such conditions may provide the key to understanding the formation of diamonds on other planets and celestial bodies, such as carbon asteroids. The Popigai crater, therefore, not only preserves the traces of an ancient cosmic catastrophe, but also opens new horizons in the field of planetary science. Each year, researchers and geologists come here to study its unique geological structures and analyze soil samples that may contain information about ancient climatic conditions. For many, this crater remains a mystery, holding secrets that humanity is just beginning to understand. The unique diamonds found here can be not only valuable for the jewelry industry, but also become an important object of scientific research, allowing us to look into the past of our planet and even into the future of other worlds. The Tunguska event occurred on June 30th, 1908, when a celestial body, presumably a meteorite, exploded in the atmosphere over Siberia's taiga. This explosion, comparable in power to several megatons of TNT, left behind astonishing devastation. Scientists estimate that it felled trees over an area of about 2,000 square kilometers, destroying more than 100,000 trees within a radius of more than 20 kilometers from the epicenter. However, despite the expected consequences of such a powerful explosion, no crater was found. This raises many questions about the nature of the event, as a celestial body colliding with Earth should leave visible traces. Research conducted in subsequent decades revealed that the explosion occurred in the atmosphere at an altitude of about 5 kilometers, which explains the absence of a crater on the surface. However, this does not make the event any less mysterious. Scientific expeditions, from the first attempts in the early 20th century to modern research, have faced numerous difficulties. The remoteness of the region, complex climatic conditions, and the lack of infrastructure create significant obstacles to detailed study. Many researchers, such as Soviet scientist Vitaly Timurov and Russian physicist Yuri Lavrentiev, have attempted to unravel the phenomenon by measuring radiation and collecting soil samples. But a full understanding of the Tunguska event remains elusive. Mysterious stories of glowing spheres and lights observed by local residents that night only add to the intrigue of this already enigmatic event. Theories about aliens, experimental technologies, and even nuclear explosions surround the Tunguska event, but none have been definitively confirmed. Scientific research continues, and each new expedition project may bring unexpected discoveries. For example, in 2009, a group of Russian and American scientists found anomalies in the soil at the supposed explosion site that could indicate high concentrations of rare minerals. Each new discovery opens up new horizons and possibilities for further investigation. The Tunguska event, shrouded in myths and legends, remains one of the most significant and unexplained episodes in the history of science. The unexplained effects of this explosion continue to generate lively interest among scientists and adventure seekers worldwide. Scientific conferences dedicated to the study of the Tunguska event attract participants from different countries, testifying to its relevance and significance. For instance, in 2020, at a conference in Irkutsk, scientists from around the world discussed the results of the latest research and proposed new hypotheses about the nature of the explosion. With each passing year, the number of theories increases, but none can explain all aspects of this phenomenon. The Tunguska event remains a symbol of scientific mystery, attracting the attention of researchers for over a century. With time, new technologies and research methods may shed light on the enigma that continues to captivate scientists and lovers of mysteries around the world. On February 15, 2013, a deafening sound echoed through the sky over Chelyabinsk, later determined to be caused by a meteor entering Earth's atmosphere. This object, weighing approximately 15 tons, reached a speed of around 18 kilometers per second, equivalent to the speed of a bullet fired from a weapon. Shortly after entering the atmosphere, the meteor burned up, creating a bright flash visible from hundreds of kilometers away. The resulting shockwave caused significant damage in the city and its surroundings. Around 700,000 windows were shattered, buildings sustained damage, and more than 1,500 people sought medical help due to injuries from glass and other debris. The Chelyabinsk meteor became one of the largest incidents involving a meteor falling in a populated area and symbolized the threat of cosmic intrusions into daily life. Search for meteor fragments began almost immediately after its fall. Groups of scientists and researchers, including astronomers and geologists, headed to Lake Shebakul, where it was believed the fragments might be located. Numerous small meteor fragments were found, with the largest weighing around 7 kilograms. These findings provided scientists with valuable data on the meteor's composition, origin, and how such objects interact with the atmosphere. Over several weeks, the meteor fragments were collected and studied, offering insights into how cosmic bodies can impact life on Earth. The meteor became a topic of discussion at scientific conferences and in the media, raising questions about safety and the possibility of preventing such incidents in the future. Since then, numerous lectures and events focused on meteors and cosmic threats have been organized in Chelyabinsk, attracting both local residents and scientists from other countries. The Chelyabinsk meteor became not just a scientific object, but also a cultural phenomenon, embodying the suddenness of cosmic threats that can strike Earth at any moment. Notably, this meteor was the first large cosmic object to be recorded and studied using modern technologies, including video recordings and sensors collected by local residents. Tsunamis are giant waves that occur as a result of underwater earthquakes, landslides, or impacts from celestial bodies such as meteoroids. These waves form when large volumes of water are suddenly displaced, often due to the movement of tectonic plates. For instance, during an earthquake of magnitude 7 or higher, the underwater part of the Earth's crust can suddenly rise or fall, generating powerful waves. In the deep ocean, a tsunami can be virtually imperceptible, with a height of just a few dozen centimeters and moving at speeds up to 80 kilometers per hour. This creates a deceptive calm. Ships and vessels on the surface may not even notice the approaching threat. However, as the wave approaches the shore and reaches shallow water, it begins to gather energy, with the wave height increasing to 30 meters or more, transforming the peaceful ocean into a destructive force. When the wave reaches the shore, it crashes with immense power, sweeping away everything in its path. The destructive power of tsunamis is evident from historical events where entire cities have been submerged. For example, the speed and strength of waves can significantly increase in narrow bays or inlets, where the wave compresses. This phenomenon is known as resonance. Tsunamis can cause not only the destruction of buildings, but also profound changes in the landscape, creating new relief forms. It is important to note that the early warning system for tsunamis, developed after the 2004 catastrophe, includes networks of sensors that detect underwater earthquakes and changes in sea level. These sensors can transmit signals to coastal stations, allowing people to evacuate before the wave arrives. Despite all the scientific and technological advancements, tsunamis remain one of the most dangerous natural disasters, capable of taking thousands of lives in a matter of minutes. In open ocean, a tsunami can pass unnoticed, but near the shore it becomes a catastrophe. For example, the maximum height of a wave can exceed 40 meters, comparable to the height of a 12-story building. Tsunamis remain one of the most complex natural threats, requiring attention and thorough study. In the Indian Ocean on December 26, 2004, one of the most devastating tsunamis in history occurred. The cause was a powerful earthquake with a magnitude of 9.0, which happened at a depth of around 30 kilometers off the coast of Sumatra in Indonesia. This earthquake caused the seabed to rise by several meters, triggering a massive wave. The tsunami generated by this seismic event moved at speeds up to 80 kilometers per hour, comparable to the speed of a jet plane. The first waves reached the shores of Sumatra just 15 minutes after the earthquake, but as the wave spread across the ocean, its power and size increased. The height of the wave varied depending on the ocean floor topography and the shape of the coastline, ranging from several meters to 30 meters or more. For example, on the coast of Indonesia, waves reached heights of up to 30 meters, while in more open waters, the wave height could be as little as 1 or 2 meters. As the wave approached the shore, it accelerated, and upon hitting land, it turned into a devastating wall of water. The tsunami struck the coasts of more than 12 countries, including Thailand, Sri Lanka, India, and the Maldives, leaving behind a trail of complete destruction. As a result of this natural disaster, more than 240,000 people died, and millions were left homeless. In some regions, such as Male, the capital of the Maldives, the wave flooded entire areas, destroying buildings and infrastructure. In Thailand, on the famous beaches of Phuket, the waves washed away restaurants and hotels, leaving only debris. In Sri Lanka, the waves destroyed coastal villages, carried away ships, and damaged ports, severely impacting the country's economy. In response to the tsunami, humanitarian organizations began providing aid to the affected, and the international community collected funds for reconstruction. This event also highlighted the need for early warning systems for tsunamis in the Indian Ocean. which became one of the priority areas for preventing such disasters in the future. The tsunami of 2004 caused catastrophic consequences for the coastal ecosystems. Mangrove forests, which served as a natural barrier to waves and provided a habitat for numerous species, were virtually destroyed. According to experts, around 60% of the mangrove forests along the Indian Ocean coast were washed away. This destruction led to a disruption of the ecosystem, as mangroves play a crucial role in protecting the coastline from erosion and maintaining the health of coastal ecosystems. Coral reefs, which are home to more than 25% of all marine species, also suffered. Studies show that more than 30% of the reefs in the tsunami zone were destroyed or severely damaged. These reefs not only serve as habitats for many species, but also protect the coast from waves, contributing to the overall preservation of the ecosystem. The saltwater that flooded agricultural lands led to severe soil salinization, making many lands unsuitable for agricultural use. For example, in the region of Mahabalipuram in India, where rice and vegetables were previously grown, yields fell by 80% in the first years after the tsunami. The landscape changes also affected coastal regions. New bays and inlets were formed, and old areas changed shape under the influence of powerful waves. The restoration of the ecosystem required a lot of time and effort. In some places, natural recovery began, but in other cases, human intervention was necessary to restore mangrove forests and coral reefs. In 2006, Indonesia launched a program to restore mangrove forests, involving the planting of more than 1 million seedlings, which helped to bring life back to the affected areas. By 2018, there was a 10 to 15% increase in coral reefs in some places, but the full recovery of these ecosystems will take decades. Gradually, nature began to return, but this process is slow and requires constant attention. The restoration of the ecosystem after the tsunami is not just a matter of time, but also the ability to adapt to new conditions. Palaco tsunamis represent ancient tsunamis that have left their traces in the geological record of Earth. Geologists studying the deposits brought by these catastrophic waves use a variety of methods to identify and interpret them. For example, in 2008, a team of geologists led by Dr. Christopher Curtis from the University of California, Santa Barbara, discovered Palaco tsunami deposits on the California coast, dating back to around 1700 years before our era. These deposits, consisting of layers of sand and clay, were found at a depth of about 3 meters below the surface and indicate powerful floods caused by tsunamis. Geologists use radiocarbon dating to determine the age of these layers, as well as analyze the mineral composition and structure of the deposits, allowing them to make conclusions about the strength and direction of the waves. Each layer of deposits can tell a story about a specific event, from the height of the wave to the time of its arrival. For example, deposits found on the coast of Japan indicate tsunamis that occurred in 2650 and 800 years before our era, when the waves reached heights of 30 meters. By analyzing geomorphological changes and erosion traces left by the waves, researchers can assess the frequency and scale of such events in the past. This knowledge is critically important for predicting future risks, especially in seismically active zones such as the Pacific Ring of Fire. In 2006, scientists from the Institute of Oceanography in Sandy Hook, New Jersey, studied deposits on the floor of the Atlantic Ocean that indicate tsunamis that occurred 8,000 years ago. They found that some soils were mixed with marine deposits, confirming the presence of powerful waves capable of moving heavy rocks and gravel. These studies help create models that predict the likelihood of tsunamis based on historical data. For example, according to scientists, in the region of Antarctica over the past 10,000 years, there have been at least 12 major tsunamis, confirming the need for monitoring such areas. Scientists also use geophysical methods, such as seismic sounding and magnetic surveys, to detect hidden Palaco tsunami deposits. In 2009, researchers from the University of Florida discovered Palaco tsunamis in the Gulf of Mexico by analyzing data from seismic instruments. They found that deposits associated with tsunamis can be located at depths of up to 500 meters below the ocean floor, opening new horizons for studying Earth's past. Thus, Palaco tsunami research not only helps understand natural processes, but also serves as a basis for developing methods of protection against possible future catastrophes. Scientific data obtained from such research form the basis for creating risk maps for coastal regions, allowing for more effective evacuation and prevention of human casualties. Scientists emphasize that understanding the history of Palaco tsunamis is a key element in preparing for future threats, as knowledge of how frequently such events occurred in the past allows for predictions about the likelihood of their recurrence. For example, based on the analysis of deposits found on the Pacific coast, the probability of a tsunami occurring every 150 years was established, significantly increasing the level of preparedness of the local population. Earthquakes are sudden and powerful underground shocks that occur due to the abrupt displacement of blocks of the Earth's crust. These displacements occur as a result of the buildup of stress in the Earth's crust. When this stress exceeds the strength of the rocks, a rupture occurs, which generates seismic waves. These waves spread in various directions from the point of rupture, known as the focus, and can travel through different layers of the Earth, changing their speed and intensity depending on the type of rock. There are several types of seismic waves. The first are P waves, which are the fastest and can travel through both solid and liquid media. Following them are S waves, which move slower and can only travel through solid materials. In addition to these waves, there are surface waves, which cause the most destructive effects on the surface, creating vertical and horizontal oscillations that can damage buildings and infrastructure. For example, during the 1994 earthquake in Los Angeles, the strength of the S waves caused significant damage in urban areas. The intensity of oscillations depends on many factors, including the depth of the focus, the distance to the epicenter, and the types of soil. Light buildings may not withstand strong shocks, while more robust structures can withstand significant loads. The unpredictability of earthquakes lies in the fact that they can occur at any time and without warning, making them one of the most dangerous natural phenomena. Scientific research shows that approximately 30,000 earthquakes occur worldwide each year, and most of them are imperceptible to humans. However, there are also catastrophic events that can result in massive human casualties and destruction. The importance of monitoring seismic activity is becoming increasingly apparent, as modern technologies allow the detection of precursors to major events, although precise forecasts remain a challenging task. Seismologists like Dr. Kenneth Hong are working on developing more accurate models that can help understand the mechanisms of earthquake occurrence and thereby enhance the level of population safety. The Great Lisbon Earthquake occurred on November 1, 1755, and is considered one of the most devastating natural disasters in European history. The earthquake reached a magnitude of 9 on the Richter scale, causing catastrophic destruction in Lisbon and its surroundings. Estimates suggest that around 30,000 buildings were destroyed, and the death toll ranged from 30 to 100,000 people. Following the earthquake, a powerful tsunami struck the coast, washing away homes and taking lives. In some areas, the water level rose by more than 20 meters. Fires sparked by the earthquake not only destroyed the remaining buildings, but also raged on for several days, exacerbating the situation. One of the first to respond to this catastrophe was the philosopher Voltaire, who began discussing the nature of evil and divine providence in his works. He questioned how such a disaster could occur in a world supposedly created by a benevolent deity. This event sparked philosophical debates about fate and free will, touching on ideas such as Leibniz's best of all possible worlds and Rousseau's questions about human nature. The earthquake led to new approaches to studying natural disasters. Seismology as a science began to develop, and one of the first to systematically study earthquakes was the Portuguese priest and scientist José Silvio, who proposed using observations of earthquakes to better understand these phenomena. After the Lisbon earthquake, the first seismic service was established, which began to record and analyze data on earthquakes. The reconstruction of Lisbon after the disaster became a massive project involving architects, engineers, and philosophers. Count of the Marquis de Pombal, who led the reconstruction, implemented new building standards that included the use of more earthquake-resistant structures, which later became the standard for construction in seismic-prone regions. These events not only changed the appearance of Lisbon, but also influenced European society, prompting a re-evaluation of views on the nature of evil and the role of humans in the world. Some philosophers, such as Immanuel Kant, began to see the earthquake as a challenge to human morality and ethics, asserting that such catastrophes could serve as lessons for humanity. Ultimately, the Great Lisbon earthquake left a deep mark on the history of Portugal and contributed to the development of modern scientific approaches to studying natural disasters. As a result, the event became the basis for creating the first maps of seismic activity, which later became an important tool for predicting and preventing the consequences of such disasters. On the night of April 20th to 21st, 1906, San Francisco was struck by a devastating earthquake with a magnitude of around 8 on the Richter scale. The epicenter was along the San Andreas Fault, which, like a malevolent thread, ran through California. The ground trembled for about a minute, but that was enough to destroy more than 25,000 buildings, leaving only piles of rubble on the city streets. Houses made of brick and wood could not withstand such pressure, and thousands of people were trapped under the debris. Meanwhile, residents tried to escape the hellish panic and chaos that reigned around them. However, this was just the beginning of the disasters, as soon after the first tremors, fires broke out in the city due to damaged gas pipes and stoves. The flames spread quickly, and as a result, more than 14,000 homes were destroyed. The fires raged for 3 days, and despite the efforts of firefighters who lacked sufficient water to extinguish the flames, many parts of the city were turned into a wasteland. Mountains of debris and burning ruins created an apocalyptic atmosphere as people struggled to save their lives and belongings in unbearable conditions. Estimates suggest that between 600 and 3,000 people lost their lives in this catastrophic event, while around 12,000 were left homeless and had to take refuge in makeshift camps set up in parks and open spaces. The city's recovery took years, and many residents left in search of a better life. San Francisco, once a thriving and vibrant city, became a symbol of destruction and fear, marking a significant milestone in the study of seismic activity and preparation for future disasters. The earthquake and subsequent fires not only changed the city's appearance, but also altered approaches to construction and urban planning, ultimately leading to the creation of new safety standards and stricter building codes. Seismic-resistant construction has become a response to devastating earthquakes that have claimed numerous lives and destroyed entire cities. Following the catastrophe in San Francisco in 1906, engineers began developing new methods for designing buildings that could withstand strong ground tremors. One of the first significant steps was the integration of damping technologies that help reduce the force of vibrations transmitted to the structure. For instance, in 1981 in Japan, after the catastrophic earthquake in Kobe, a system of damping pads was developed, which are installed under the foundations of buildings, significantly reducing the level of vibrations. These pads are made from special polymer materials that have high elasticity and can absorb the energy generated during earthquakes. Engineers also began using flexible structures that allow buildings to bend rather than break. This was particularly important for tall skyscrapers that are subject to strong oscillations. For example, the famous Torre Satellite skyscraper in Mexico City, built in the 1990s, became a model for the use of such technologies. Its frame includes special steel ribs that provide stability and resistance during earthquakes. In the 2000s, other innovations emerged, such as the use of superelastic materials and carbon fibers, which significantly increased the strength of structures. For example, in 2000 in Los Angeles, the Tower of the World was built, which uses carbon fibers in its columns, reducing the weight of the structure and enhancing its stability. It is also worth mentioning the creation of specialized monitoring systems that allow for the early prediction and analysis of seismic events. These systems operate based on data from seismometers located worldwide and can warn of an impending threat several seconds before the onset of tremors. This time can save lives, allowing people to evacuate and shut down critical systems such as gas and electricity. According to the Japan Meteorological Agency, the implementation of such technologies has reduced the number of casualties by 30% since the 1990s. Ultimately, seismic-resistant construction continues to evolve, integrating new research and technologies, enabling the creation of safer and more earthquake-resistant buildings that can withstand even the strongest ground tremors, such as the Abu Dhabi skyscraper, 180 meters tall, built in 2003, which demonstrates a high degree of resistance thanks to the use of the latest design and construction technologies. Early warning systems for earthquakes consist of complex networks of seismometers that continuously record surface movements and analyze data in real time. For instance, in Japan, where earthquakes occur with alarming regularity, one of the most advanced early warning systems in the world operates. This system, established in 2008, includes over 100,000 seismometers distributed throughout the country, which transmit data to the Seismic Monitoring Center in Tokyo. The data processing algorithms used in this system allow for the rapid determination of the location and magnitude of an earthquake in just a few seconds. The system analyzes how quickly seismic waves reach various points and makes predictions about when they will reach populated areas. If the magnitude exceeds a certain threshold, the system automatically sends an alert signal. For example, during the devastating earthquake off the coast of Fukushima in 2011, the system was able to warn residents of the impending danger just a few seconds before the destructive tremors began. This time can be crucial, allowing people to take shelter in safe places such as designated shelters or under sturdy tables. In cities like Tokyo, when an alert signal is received, the system automatically activates warning messages through city loudspeakers and sends SMS messages to residents' mobile phones. This race against time becomes critically important, as every second can save lives. A study conducted in 2009 showed that if the warning system had been activated a few seconds earlier during the 2010 earthquake in Haiti, a significant number of lives could have been saved. The effectiveness of such systems depends not only on technology, but also on the preparedness of the population. In Japan, regular evacuation drills are held, which help people react quickly in the event of a real earthquake. These drills demonstrate the importance of being prepared for emergency situations and knowing what actions to take. In the 21st century, technology continues to advance, and researchers are working on new methods, such as using artificial intelligence for more accurate earthquake prediction. For example, in 2020, a group of scientists from the University of California, Berkeley, developed an algorithm that analyzes data from seismometers and can predict earthquakes with an accuracy of up to 10 seconds. This time may seem insignificant, but in the face of an impending disaster, it becomes decisive. Considering the scale of destruction that earthquakes can cause, it becomes clear how important every second is. Given that the most powerful earthquakes can cause damage over hundreds of square kilometers, early warning systems are not just a recommendation, but a necessity for the safety of the population. The climate of Earth is a dynamic system that is constantly in motion and change. Throughout the planet's geological history, significant temperature fluctuations have occurred, which can be conditionally divided into greenhouse states and ice age periods. During greenhouse epochs, global temperatures could be tens of degrees higher than today's, allowing tropical forests to grow even in areas now covered by ice. For example, around 100 million years ago, during the Cretaceous period, Earth's temperature reached approximately 30 degrees Celsius, and sea levels were hundreds of meters higher than today. This created ideal conditions for diverse flora and fauna, including large dinosaurs and giant marine reptiles like plesiosaurs. In contrast, during ice ages, which followed warmer epochs, the climate significantly cooled and polar ice caps expanded, covering much of North America and Europe. During these times, sea levels could drop by more than 100 meters, altering the planet's geographical map and facilitating the formation of land bridges like the Bering Strait, through which animals and people migrated. These cycles of climate change have occurred over millions of years, and their impact on ecosystems was immense. It is important to note that such climate changes occur under the influence of various factors, including volcanic activity, changes in solar radiation, and variations in Earth's orbit, known as Milankovitch cycles. Volcanic eruptions, for instance, can release enormous volumes of carbon dioxide and sulfur into the atmosphere, leading to a greenhouse effect, or, conversely, its weakening. Over the past 2 million years, Earth has experienced at least 5 major ice ages, each lasting thousands of years and having a significant impact on biological diversity. These ice ages and interglacial periods created conditions under which many species survived, adapted, and evolved, while others went extinct. The constant changeability of climate is an integral part of Earth's history, clearly demonstrating that the planet's climate system is not a static structure, but a living, evolving organism subject to numerous influences. Over the past 100 years, humanity has witnessed how anthropogenic factors, particularly carbon emissions, have altered this balance. For example, since the beginning of the Industrial Revolution, the level of carbon dioxide in the atmosphere has increased by more than 180 parts per million, causing concern among scientists about the potential consequences for the climate system. This climate change, driven by human activity, occurs against the backdrop of natural fluctuations, adding complexity to the study of our planet's future. Nevertheless, in the face of such changes as temperature rise and changes in weather patterns, it is important to understand that Earth has already experienced numerous changes, and our role in this process will determine how we adapt to the future. Observing the history of Earth's climate, one can see that every 100,000 years, temperature has changed by 10 to 20 degrees, illustrating the degree of variability in the climate system. The Paleocene-Eocene thermal maximum, which occurred approximately 56 million years ago, was one of the most significant climatic events in Earth's history. During this period, the surface ocean temperature rose by 5 to 8 degrees Celsius, leading to dramatic changes in ecosystems both on land and in the sea. This warming occurred against a backdrop of increasing concentrations of carbon dioxide in the atmosphere, which could have been linked to volcanic activity and the release of carbon from oceanic sediments. Surface ocean temperatures reached critical levels, altering the chemical composition of water and reducing oxygen levels, which was catastrophic for many marine organisms. Mass extinctions of marine species, such as certain groups of shellfish and corals, occurred as they were unable to adapt to the rapidly changing conditions. Terrestrial ecosystems were also affected. Plant ranges shifted significantly. Tropical and subtropical forests expanded into higher latitudes, while colder plant species gradually retreated. The emergence of new ecosystems altered the behavior and distribution of animals, such as mammals, which began to adapt to new conditions by developing various survival strategies. Some groups of mammals, like primates, actively expanded and migrated to previously inaccessible regions, while others, like large herbivores, suffered from food shortages due to changes in vegetation. The period also saw more favorable conditions for reptiles and insects, leading to their rapid reproduction and diversification. This time was crucial for the emergence of the earliest ancestors of modern mammals, such as primitive forms of whales and elephants, which began to actively colonize new ecological niches. Increased temperatures caused some species previously adapted to colder conditions to rapidly disappear, while new species took their place. For example, the ranges of some fish species shifted northward into cooler waters, as confirmed by fossil remains and paleontological findings. Climate changes affected animal migration routes, which in turn altered ecosystems and created new habitats. It is important to note that the Paleocene-Eocene thermal maximum not only demonstrated the ability of ecosystems to adapt to extreme conditions, but also played a key role in the evolution of life on Earth, forming new biological communities and ecosystems that shaped the planet's appearance for millions of years to come. During the Paleocene-Eocene thermal maximum, which occurred approximately 56 million years ago, a massive release of methane from methane hydrates on the ocean floor played a crucial role in climate change. Methane hydrates are crystalline structures containing methane that form at high pressure and low temperature. As ocean temperatures began to rise, this led to the melting of methane hydrates, which in turn released enormous volumes of methane into the atmosphere. Studies indicate that the amount of methane released into the atmosphere could have reached levels up to 200 billion tons, equivalent to emissions over millions of years. Methane is a potent greenhouse gas, 25 times more effective than carbon dioxide in trapping heat in the atmosphere over a century. These releases created a positive feedback loop. Initial warming led to the release of methane, which enhanced the greenhouse effect and further increased temperatures. With each additional degree of warming, more methane hydrates decomposed, and the process intensified. This created a chain reaction that temporarily destabilized the planet's climate system, leading to a sharp increase in global temperatures by up to 10 degrees Celsius. It is important to note that such temperature fluctuations ultimately altered rainfall patterns and affected ecosystems, contributing to the extinction of some species and the emergence of new ones. This period also coincides with the rapid diversification of mammals, which began to fill ecological niches left vacant by the extinction of dinosaurs. As a result, by the end of the Paleocene-Eocene thermal maximum, Earth's ecosystems underwent significant changes that laid the foundation for modern biological diversity. Snowball Earth is a hypothetical period in the history of our planet when glaciers covered almost its entire surface, including equatorial regions. This period, which according to geological data could have occurred around 700 million years ago, is known as global glaciation. During this time, the surface temperature of Earth significantly dropped, and oceans froze almost to the equator, creating a world in which photosynthesis almost completely ceased. Such climatic conditions were catastrophic for life. The diversity of ecosystems sharply decreased, and life persisted only in isolated refuges. Hot springs and deep-sea hydrothermal vents became the last strongholds for microorganisms and some organisms that survived in extreme conditions. In particular, such places as hydrothermal vents on the ocean floor became homes for ecosystems based on chemosynthetic bacteria that used sulfur and methane compounds for energy production. These bacteria served as the basis for food chains where organisms like tube worms and mollusks, adapted to life in the absence of sunlight, lived. At this time, when Earth was covered with a thick layer of ice, oceans turned into frozen wastelands where water temperature could drop to -40 degrees Celsius. In such conditions, survival became a true art. An important aspect of this period is that on Earth there was a sharp decrease in carbon dioxide in the atmosphere, which in turn contributed to further cooling of the climate. This phenomenon could also be related to the activity of ancient plants that absorbed carbon dioxide, but could not produce enough oxygen to sustain life in such conditions. Geological evidence, such as carbon and oxygen isotope deposits, confirms the presence of such extreme climatic changes. Research shows that Snowball Earth could have lasted for millions of years, and it was only with the onset of new climatic conditions, such as global warming, that life began to recover. Scientific models suggest that it was during this period that significant changes in the chemical composition of oceans occurred, which contributed to the appearance of new forms of life. Each of these stages of glaciation and subsequent warming left its mark in the geological history. For example, on the continent of Greenland, there were large glaciers that, according to estimates, could have reached a thickness of up to 3 kilometers. The melting of these glaciers led to a rise in the global sea level by tens of meters, which contributed to the formation of new ecosystems on coasts and in coastal zones. There are also theories that the conditions of Snowball Earth could have been a catalyst for the appearance of multicellular organisms, as new ecosystems offered a variety of ecological niches. The diversity of life forms that we observe today might not have been possible without those harsh conditions when the planet was practically devoid of vegetation and warmth. This period left an indelible mark on the history of Earth and continues to be the subject of active research. During the Earth's coldest times, significant geological processes occurred, ultimately leading to dramatic changes in climate. Volcanic activity began to intensify, particularly in regions such as Oceania and Iceland. Volcanic eruptions that took place around 150 million years ago released massive amounts of carbon dioxide, methane, and sulfur gases into the atmosphere. These gases, with their high greenhouse potential, began to accumulate in the atmosphere, creating conditions for rapid climate change. Simultaneously, tectonic processes activated rift zones where underwater volcanoes released hot gases and minerals, adding more carbon dioxide to the air. Gradually, with each new eruption, the concentration of greenhouse gases reached critical levels, intensifying the greenhouse effect. This can be compared to an accelerating avalanche. Small changes accumulate until they cause a devastating effect. As a result, the Earth's surface temperature began to rise, leading to rapid melting of the ice sheets covering the continents. Around 100,000 years ago, due to the increase in global temperature, glaciers began to retreat, exposing lands that had been buried under thick layers of ice. This transition from the Ice Age to warmer conditions was dramatic. In some places, the rate of melting reached 20 centimeters per year, leading to the formation of large lakes and new ecosystems. Water released from melting glaciers filled lowlands, and the melting of ice caused a rise in sea levels. This process was followed by changes in ecosystems that began to colonize the newly exposed territories, contributing to the development of new plant and animal species. As a result of this chain reaction, conditions for global warming were created, which continued for thousands of years. It is important to note that this period was the basis for the emergence of the first multicellular organisms, which began to evolve in the new ecosystems. For example, around 60 million years ago, the first coral reefs appeared on Earth, becoming important ecosystems for many marine creatures. This transition in the climate system from a frozen world to tropical conditions showed how quickly and dramatically ecosystems can change under the influence of geological and atmospheric processes. Scientific research indicates that during that period, the level of carbon dioxide in the atmosphere could reach 3,000 parts per million, which is many times higher than current levels. In the Anthropocene, which began roughly in the middle of the 20th century, humanity has become the dominant factor contributing to mass species extinction. Research indicates that the rate of animal and plant extinction in this period exceeds the natural background extinction rate by tens and even hundreds of times. While previously, on average, 1 to 2 species disappeared every million years, today we observe the extinction of up to 30 species every 10 years. This phenomenon has become possible due to numerous factors related to human activity, including the destruction of natural habitats, climate change, environmental pollution, and excessive exploitation of natural resources. Scientists estimate that by the end of the 21st century, between 30 and 50% of all species may become vulnerable or extinct if current trends continue. The uniqueness of the current situation lies in the fact that one species, Homo sapiens, has become the cause of global ecological transformation that affects not only individual ecosystems, but the entire planet. Unlike past mass extinctions, which were caused by natural disasters such as asteroid impacts or volcanic eruptions, modern extinction is directly caused by human activity. For instance, deforestation for agriculture and urbanization leads to the destruction of biomes where thousands of species live. Agricultural practices based on monoculture destroy the diversity of flora and fauna, which in turn disrupt ecosystem services such as pollination and soil fertility maintenance. Additionally, climate change, caused by greenhouse gas emissions, leads to warming and changes in weather conditions, further exacerbating the situation. Scientific models show that if temperatures continue to rise, many species will not be able to adapt to the new conditions, and their populations will rapidly decline. For example, coral reefs, which are among the most biodiverse ecosystems, are currently suffering from bleaching and death due to increased water temperature and ocean acidity. Furthermore, international agreements, such as the Convention on Biological Diversity, are not always effective in protecting vulnerable species. As a result, we now face a unique situation where mass extinction is occurring not only due to natural factors, but also under the influence of one species that paradoxically should be the guardian of nature. These changes already have a significant impact on food security, human health, and the economy. For example, the disappearance of pollinators like bees can lead to a decrease in the yield of many agricultural crops, affecting food supplies and prices. Consequently, the Anthropocene is an era in which the resilience of the biosphere is threatened, and if humanity does not take decisive action, the consequences will be catastrophic. Research shows that to prevent further loss of biological diversity, it is necessary to reduce carbon emissions by at least 45% by the 2030s and restore degraded ecosystems. In Australia during the Holocene epoch, there was a mass extinction of megafauna, including giant marsupials, large reptiles, and birds that inhabited the continent before the arrival of the first humans. Around 50,000 years ago, when modern humans began to settle Australia, they encountered a unique ecosystem that had evolved in isolation over millions of years. Evolution led to the appearance of large herbivores such as the Megatherium, a giant lizard up to 4 meters long, and Diprotodon, the largest known marsupial, weighing up to 2 tons. These animals had no natural predators except possibly large eagles, making them particularly vulnerable to the new predator, humans. The first Australians, as they settled the continent, used fire for hunting and landscape management, which was one of the factors contributing to the extinction of megafauna. For example, archaeological findings show that people used fire to attract animals to places where they could be more easily caught. As a result of this hunting pressure and changes in the ecosystem, by 10,000 years ago, there was a significant decline in the populations of large herbivores. This not only altered food chains, but also affected vegetation and fire regimes on the continent. Since large herbivores like Diprotodon played a crucial role in maintaining the ecosystem, their disappearance led to changes in the structure of vegetation. Without a mechanism to control the growth of grasses and trees, there was an increase in shrubs and small-leaved plants, altering the familiar landscape. The disappearance of large animals also changed fire regimes. Without regular consumption of vegetation by large herbivores, forests became more susceptible to frequent and intense fires. These changes affected many other species that depended on these ecosystems and led to further reduction in biodiversity. As a result, the ecosystem of Australia began to shift towards drier and less diverse landscapes, forming the basis for the continent's modern ecosystems. For instance, many plant species that were once widespread were replaced by more drought-resistant species. This process was not only due to the extinction of megafauna, but also to the climate change that occurred during the same period. The impact of human activity on the Australian ecosystem during the Holocene epoch had long-term consequences that continue to be felt today. For example, archaeologists have found numerous remains of megafauna, such as Diprotodon and Megatherium bones, in places where ancient human camps were located, confirming the link between human activity and the extinction of these species. The dodo, or dronte, was a flightless pigeon that inhabited the island of Mauritius, which was discovered by Europeans in the 16th century. The first records of the dodo date back to the 1680s, when Portuguese sailors spotted it on the coast. These were large birds, weighing up to 25 kilograms, with a distinctive rounded body and short wings. Due to the absence of natural predators on the island, dodos had no fear of humans and seemed unaware of the danger, making them easy targets for hunters. With the arrival of the first colonists, mainly Dutch settlers, in 1601, the mass slaughter of dodos began. Dutch sailors, seeking to provide themselves with food, actively hunted these birds, unaware that their hunting could lead to their extinction. Around the same time, introduced species such as pigs, cats, and rats were brought to the island, which began to eat the dodo's eggs, which were laid on the ground. As a result, the dodo population began to decline rapidly. By 1618, the dodo was already considered a rare species, and by 1630, they had disappeared forever. Scientific research shows that within less than 100 years after the island's discovery, the dodo became a symbol of tragic misunderstanding of the value of unique species and their vulnerability to new threats. Important finds, such as dodo remains, were discovered in places where their nests once were, confirming how humans destroyed the natural habitat. The dodo became one of the first known cases where human activity led to the complete extinction of a species, serving as a crucial lesson for future generations. The 18th century marked a time when people began to recognize the consequences of their actions, but unfortunately, it was too late for the dodo. Scientific research conducted in the 20th century revealed that dodos were not only an essential part of Mauritius's ecosystem, but also a unique example of evolution and adaptation to isolated conditions. The remains of dodos found in various places help scientists understand how species developed in limited habitats and what factors contributed to their extinction. Contemporary methods of preserving endangered species are becoming increasingly diverse and complex as humanity recognizes the need to protect the remaining representatives of unique ecosystems. Captive breeding programs have already proven effective, as demonstrated by the case of the black-footed ferret, Mustela nigripes, which was on the brink of extinction in the 1990s. Scientists from the Institute of Wildlife Ecology in the United States began a captive breeding program, which resulted in the black-footed ferret population increasing from fewer than 30 individuals to more than 1,000 in the wild by 2021. A key element of this program was creating conditions as close as possible to natural ones, including the use of specialized enclosures and programs to enhance the survival of young individuals. Genetic material cryopreservation represents another breakthrough in the field of biodiversity conservation. Scientists at the Smithsonian Institution in Washington are actively collecting and freezing eggs, sperm, and embryos of rare species, including the Jamaican iguana, Cyclura coli. In the 21st century, they have created the largest genetic material collection in the world, which can be used in the future to restore populations. Restoring ecosystems is becoming another important strategy, as it allows natural communities to return to a state close to their original condition. An example is the project to restore wetlands in California, which began in 2002. Scientists and ecologists worked together to restore more than 300 hectares of natural wetlands, which contributed to the increase in local species such as red-listed ducks and fish. Environmental organizations, such as the World Wildlife Fund, WWF, actively support such initiatives by funding research on the interactions between species and their habitats. Within the International Biodiversity Protection Program, launched in 2017, more than 100 countries signed an agreement on joint actions to prevent new extinctions. These measures include the creation of protected natural areas and programs to educate local communities about the importance of nature conservation. For example, in Indonesia, local residents participate in the protection of ancient forests, receiving funding for the conservation of rare species. Thus, contemporary methods of preserving endangered species are becoming more integrated and multifunctional, allowing not only to prevent the extinction of individual species, but also to restore entire ecosystems. According to the UN, more than 1 million animal and plant species are at risk of extinction in the 21st century, highlighting the importance of these efforts. Anthropogenic climate change occurs due to human activities that result in a significant increase in the concentration of greenhouse gases in the atmosphere. The primary culprit of this process is carbon dioxide, which is released in enormous quantities during the burning of fossil fuels such as coal, oil, and natural gas. Over the past few decades, the amount of CO2 in the atmosphere has risen from approximately 300 to over 400 parts per million, reaching a record level in the last several million years. This gas, along with methane and nitrous oxide, creates a greenhouse effect by trapping infrared radiation that the Earth emits into space. The increase in the concentration of these gases intensifies the greenhouse effect, leading to a rise in the average global temperature. This temperature increase causes the melting of glaciers and polar ice, which raises sea levels and threatens coastal regions. For instance, over the past 40 years, the Greenland ice sheet has lost around 30 trillion tons of ice, one of the most striking consequences of anthropogenic climate change. The increase in temperature also accelerates water evaporation, affecting the water cycle and leading to more frequent and intense droughts in some regions and floods in others. This creates an imbalance in ecosystems and threatens food security, as agricultural crops become more vulnerable to weather changes. Additionally, climate change affects biological diversity. Many animal and plant species struggle to adapt to the rapid changes in their environment and face the risk of extinction. For example, coral reefs, which support numerous marine ecosystems, are suffering from bleaching due to rising water temperatures and ocean acidification. Scientific research shows that corals lose their symbiotic algae, necessary for their survival, leading to mass coral death. Furthermore, anthropogenic climate change contributes to an increase in the frequency and intensity of extreme weather events, such as hurricanes and tornadoes, posing a serious threat to human lives and infrastructure. For example, Hurricane Katrina in 2005 was one of the most devastating hurricanes in U.S. history, claiming the lives of more than 1,000 people and leaving billions of dollars in damage. This growing imbalance in the planet's climate system underscores the need for urgent measures to reduce greenhouse gas emissions and transition to sustainable practices. While some countries are actively adopting renewable energy sources such as solar and wind power, others continue to rely on fossil fuels, exacerbating the problem. Relatively small countries like Norway have achieved success in transitioning to electric vehicles, while large countries like India and China continue to intensively exploit coal mines. As a result, global efforts to combat climate change become more complex and contradictory, requiring international cooperation and coordinated action. Considering these facts, it is clear that anthropogenic climate change has a significant impact on the entire planet. The melting of Arctic ice in recent decades has become one of the most alarming trends observed in climatology. Since 1979, the area of sea ice in the Arctic Ocean has decreased by approximately 50%, and this reduction shows no signs of stopping. According to the National Oceanic and Atmospheric Administration, NOAA, in 2020, the minimum area of ice reached an all-time low of 3 million square kilometers. This melting process is not only due to the increase in air temperature, but also due to changes in the reflectivity of the surface. Ice that once reflected up to 90% of solar radiation is now replaced by open water, which absorbs up to 90% of solar radiation. This creates a positive feedback loop. The less ice there is, the higher the temperature, which in turn leads to even more melting. As a result, the temperature in the Arctic is rising at twice the rate of the global average, with catastrophic consequences for local ecosystems. Polar bears, which rely on ice for hunting seals, are facing difficulties in finding food. Their populations are declining, making them more vulnerable to extinction. Indigenous communities, such as the Inuit, are also experiencing changes in their traditional ways of life. Climate change affects animal migration, reducing access to familiar food and water sources. A study conducted by the University of Alberta in 2009 showed that climate change has a negative impact on hunting and fishing, leading to economic difficulties for these communities. The increase in the number of storms and changes in weather patterns are becoming the norm, further complicating the lives of local residents. As a result, adaptation to new conditions has become critically important for the survival of both animals and people. For example, some communities have begun to develop alternative food sources, such as aquaculture, to compensate for the decline in traditional fishing yields. The situation is exacerbated by the fact that, according to projections, by the end of the 21st century, summer ice in the Arctic may disappear completely, leading to even more serious consequences for ecosystems and the climate as a whole. Changes in sea ice also affect global oceans, as melting ice leads to sea level rise. In 2017, scientists from the University of Colorado estimated that sea level has risen by 3 millimeters per year over the past 20 years, leading to the flooding of coastal areas worldwide. This poses a threat to millions of people living in low-lying regions. With each passing year, the impact of Arctic ice melting becomes more apparent, and new scientific research only underscores the severity of this problem. Glaciers in Greenland and Antarctica are undergoing massive changes that have serious consequences for the global climate. In Greenland, according to NASA data, the average rate of glacier melt increased by 30% from 2003 to 2018. Ice sheets are losing their stability, as evidenced by the rapid acceleration of outlet glaciers. For example, the Ilulissat Glacier, one of the most famous in Greenland, began moving at a speed of around 7 kilometers per year in 2006, making it one of the fastest-moving glaciers. This movement is linked to the increase in water temperature in coastal areas, which reaches critical levels, causing ice to melt from below. The situation in Antarctica is no less alarming. Data collected in 2013 showed that the rate of glacier melt in West Antarctica has doubled over the past 10 years. In particular, the Thwaites Glacier, known as the Sleeping Giant, is losing ice at a catastrophic rate, and, according to scientists, if it were to completely melt, sea levels could rise by 3 meters. This is not just a matter of numbers, it's a threat to coastal cities like New York and Shanghai. Each year, giant icebergs, weighing millions of tons, break off from glaciers, forming massive floating islands. In 2017, one of the largest icebergs, named A68, broke off from the Larsen C Glacier with an area of around 5,800 square kilometers, comparable to the size of the island of Cyprus. These icebergs do not just float, they become part of the global ecosystem, influencing ocean currents and climate conditions far from the poles. Scientific research shows that such changes can have unexpected consequences for marine flora and fauna, including changes in the migration patterns of fish and marine mammals. In recent decades, the rates of glacier melt have become increasingly alarming, making polar regions not only witnesses but also active participants in global climate change. If current trends continue, by the end of the 21st century, sea levels could rise by 1 meter, affecting millions of people worldwide. Rising sea levels are becoming one of the most serious threats to coastal cities and island nations. The melting of glaciers, particularly in Greenland and Antarctica, is exacerbating the situation. According to NASA estimates, Greenland loses between 300 and 400 billion tons of ice annually, while Antarctica loses more than 200 billion tons. This results in the sea level rising by an average of 3.5 millimeters per year. But in some regions, this figure can reach 8 millimeters. Thermal expansion of water also contributes to this. As ocean water temperature increases, it expands, further raising sea levels. the vulnerability of coastal territories is increasing, as such conditions could lead to flooding of low-lying areas where many people reside. For instance, in Bangladesh, where the population exceeds 80 million, around 30 million people may be at risk of flooding by the middle of the 21st century. Island nations such as the Maldives and Tuvalu are already facing the real threat of disappearance, as their average elevation above sea level is only 1 to 2 meters. These countries are forced to adapt their infrastructure by investing in protective structures such as dams and drainage systems to prevent flooding. In the Maldives, for example, the government has already begun constructing artificial islands to relocate the population, but the cost of such projects can be enormous, reaching billions of dollars. The migration of populations from flood-prone areas is becoming a pressing issue. By the end of the 21st century, up to 100 million people may become climate refugees, creating additional social and economic problems. In such circumstances, it is necessary to develop new adaptation strategies, including the creation of sustainable urban infrastructure and improvement of flood warning systems. It is important to note that flooding of coastal territories not only threatens human lives, but also destroys ecosystems such as mangroves, which play a crucial role in protecting shores from erosion and serve as habitats for numerous species. Currently, in 32 countries around the world, work is underway to develop climate change adaptation plans that include both construction initiatives and new forms of water resource management. It is expected that by the 25th year, the sea level could rise by 1 meter, affecting around 31% of all coastal cities. The change in precipitation patterns due to global warming is becoming increasingly noticeable and has serious consequences for ecosystems and human life. Research conducted by the Intergovernmental Panel on Climate Change shows that as the average global temperature has risen by 1 degree Celsius since the beginning of the 20th century, there has been a significant shift in the distribution of precipitation. In some regions, such as Eastern Africa and the southern part of the United States, droughts are becoming more frequent and intense. For example, in Kenya, since 2012, the level of precipitation has decreased by 30%, leading to the destruction of agriculture and food shortages for millions of people. At the same time, in other regions, such as Southeast Asia and some parts of Europe, there are more intense rains and floods. In 2018, Indonesia experienced one of the most destructive floods in its history, when the water level in the Citram River rose by 4 meters in just a few hours, flooding over 150,000 homes and leaving tens of thousands of people homeless. These extreme climate conditions are becoming more unpredictable, making it difficult to adapt using traditional agricultural methods. For example, farmers in southern Europe, where the average annual temperature has risen by 1.5 degrees since the year 2000, are facing new challenges. In conditions of frequent droughts, they are forced to switch to less water-intensive crops, which reduces their income. In cities like New York, the increase in precipitation intensity leads to the overflow of stormwater systems, causing street flooding and the destruction of infrastructure. As a result, cities need to rethink their water resource management strategies to prevent catastrophic consequences. Scientific research indicates that by 2030, the number of extreme precipitation events could increase by 25%, compared to the levels of the 2000s, making adaptation even more challenging. Various countries are already implementing new technologies, such as rainwater harvesting systems and climate-resilient agricultural practices. But despite these efforts, the increasing unpredictability of weather conditions poses a threat not only to the economy, but also to social stability. For example, in Bangladesh, where annual floods annually inundate millions of hectares of agricultural land, local authorities have begun implementing projects to create climate-resilient settlements. However, in the face of constant climate change and population growth, these measures may prove insufficient. According to the World Meteorological Organization, by the end of the 21st century, the global number of extreme weather events is expected to increase by 80%, which will threaten food security and water resources in the most vulnerable regions. Geoengineering is a concept that involves deliberate intervention in Earth's climate system to counteract global warming. The idea is that humanity can employ various methods to reduce planetary temperature, control climatic processes, and ultimately minimize the impacts of climate change. For instance, a study conducted in 2015 by a group of climate scientists from the US National Oceanic and Atmospheric Administration found that inaction in the face of rising temperatures could lead to ecological disasters threatening billions of people. However, experience has shown that interfering with complex natural systems can result in unforeseen consequences. The question of whether we are willing to take such risks becomes increasingly pressing, especially given the growing scientific evidence of potential side effects. In 2017, an article published in the journal Environmental Research Letters warned of possible negative consequences, including changes in meteorological patterns and ecosystems that could arise from climate manipulation. In this context, geoengineering raises numerous ethical questions. To what extent do we have the right to interfere with nature, and who will be responsible for any adverse effects? Scientists like Professor Kevin Anderson of the University of Manchester argue that it is crucial to carefully weigh the risks associated with geoengineering before making any decisions. While some researchers believe we should use all available tools to combat climate change, others caution that this could divert attention from more sustainable solutions, such as reducing carbon emissions and transitioning to renewable energy sources. There are even proposals for creating international agreements to regulate the use of geoengineering to prevent potential conflicts and ensure that such technologies are used responsibly. It is important to note that in the 20th century, humanity faced the consequences of unpredictable interventions, such as the use of chlorofluorocarbons, which led to the depletion of the ozone layer. Therefore, humanity faces a complex choice: to take the risk and use geoengineering, or to continue with inaction and accept the catastrophic consequences of global warming. Thus, geoengineering is not just a technical problem, but also a deep ethical and philosophical question that requires broad discussion and analysis. According to data from the World Economic Forum in 2020, climate change has become one of the main threats to humanity, underscoring the need for urgent action in this area. Technology for dispersing aerosols in the stratosphere, known as solar geoengineering, offers a solution for temporarily reducing global temperature, creating an effect similar to volcanic eruptions. Volcanic eruptions release massive amounts of sulfur into the atmosphere, leading to the formation of sulfate aerosols that reflect solar radiation and thus lower the surface temperature of the Earth. For instance, the eruption of Mount Pinatubo in the Philippines in 1991 caused global cooling for several years, with a temperature drop of 0.5 degrees Celsius. To artificially create such an effect, various methods of delivering aerosols to the upper layers of the atmosphere are being studied, including aircraft, high-altitude balloons, and even rockets. One of the most discussed projects is the use of modified aircraft to disperse aerosols at an altitude of around 24 kilometers, which allows for effective distribution of materials throughout the stratosphere. Research shows that to achieve a noticeable effect, the annual release of 20 to 30 megatons of sulfate aerosols is required. However, this technology is not without risks. Changes in precipitation are one of the main problems, as the dispersion can lead to changes in rainfall patterns, resulting in droughts in some regions and floods in others. For example, modeling shows that the introduction of aerosols could reduce rainfall in tropical regions by 20%. There is also the danger of ozone layer destruction, which could increase ultraviolet radiation on the Earth's surface and have negative consequences for human health and ecosystems. Research indicates that sulfates can interact with ozone, reducing its concentration, which in the long term could increase the risk of skin cancer and cataracts. Ethical and ecological questions also remain open, as altering one element of the climate system can lead to unpredictable consequences in others. In 1986, at the International Climate Change Conference in Toronto, scientists already raised questions about the possible consequences of such interventions. The dispersion of aerosols in the stratosphere is a subject of debate among scientists and ecologists, as even a temporary solution can create long-term problems, requiring a comprehensive approach to climate change and a thoughtful analysis of all possible alternatives. Technologies for capturing and storing carbon represent one of the most ambitious and complex projects of our time, requiring the creation of infrastructure comparable to the oil industry, but with a completely different goal: not extracting carbon from the Earth, but returning it back into the planet's depths. Direct capture of carbon dioxide from the atmosphere is achieved using various technologies, among which the direct air capture (DAC) method stands out. This process involves the use of chemical reagents that bind CO2, allowing it to be subsequently separated for further storage. For example, the company Climeworks, founded in 2012 in Switzerland, has developed installations that can capture up to 4,000 tons of carbon dioxide per year using special filters. It is important to note that effective capture requires a significant amount of energy, which implies the use of renewable sources such as solar and wind power plants. One of the key stages after capture is the process of binding CO2, which includes its compression and conversion into stable forms such as carbonates, thus preventing its re-release into the atmosphere. For instance, in 2020, an installation in Iceland called CarbFix was launched, which turned carbon dioxide into minerals by injecting it into basaltic rock formations. This process not only isolates carbon, but also contributes to the creation of new minerals, making it environmentally safe. Long-term storage of carbon requires the creation of geological repositories capable of holding CO2 for thousands of years. For example, in the United States, the company Occidental Petroleum, through its subsidiary 1.5, plans to create the world's largest carbon storage facility based on DAC technologies in Texas, capable of capturing and storing up to 20 million tons of carbon per year. Achieving such scales requires not only funding in the tens of billions of dollars, but also the development of new technologies and the creation of international standards and regulations. According to experts, to achieve the goals of the Paris Agreement, it will be necessary to capture at least 1 billion tons of CO2 per year by mid-century, which implies not only the development of technologies, but also global coordination of efforts. It is important to note that this process is not a panacea and should be combined with other measures to reduce emissions. But it can play a key role in the fight against climate change. According to the World Bank, by 2030, investments in carbon capture technologies could reach $100 billion. In this context, the creation of infrastructure for capturing and storing carbon becomes not just a challenge, but a necessary step towards ensuring a sustainable future. Natural solutions for carbon sequestration, such as reforestation, wetland restoration, and marine ecosystem restoration, are becoming key components of the global strategy to combat climate change. Forests, according to the Food and Agriculture Organization of the United Nations, absorb around 12 billion tons of carbon annually, equivalent to the annual carbon emissions from more than 2 billion cars. Reforestation not only promotes carbon sequestration, but also plays a crucial role in preserving biodiversity. For example, the reforestation project in Brazil, which began in 2005, has led to the restoration of over 1 million hectares of tropical forests, contributing to the increase in the populations of unique species such as the red macaw and jaguar. Wetlands, in turn, are among the most effective natural carbon sinks. They can store carbon in the form of organic matter in their peat soils. According to the World Wildlife Fund, 1 hectare of wetland can absorb up to 10 tons of carbon per year. Wetland restoration in Europe, for instance, as part of the Ecosystem Restoration Project initiated in 2010, has increased the area of wetlands by more than 30,000 hectares, significantly improving water quality and reducing the risk of flooding in the region. Healthy marine ecosystems, such as mangrove forests and seaweed, also play a significant role in carbon sequestration. Research shows that mangrove forests can absorb up to 4 times more carbon per unit area compared to tropical forests. For example, the Mangrove Restoration Project in Indonesia, started in 2015, has led to the restoration of over 50,000 hectares of mangroves, not only contributing to the fight against carbon footprint, but also providing local communities with additional sources of income through fishing and ecotourism. Healthy ecosystems provide numerous other ecological services, such as water regulation and soil erosion prevention. For example, the restoration of river ecosystems in China as part of the Blue River program has led to an 80% reduction in erosion and an improvement in the quality of water in rivers. These data emphasize that investments in ecosystem restoration not only contribute to combating climate change, but also create sustainable conditions for human life. In the near-Earth space, there are objects of various sizes that pose a potential threat to Earth. Each year, more than 20,000 meteoroids burn up in the atmosphere of our planet, but only a small fraction of them can be observed and recorded. For example, in 2003, a meteorite with a diameter of about 18 meters passed over Chelyabinsk, Russia, causing an explosion with a power of approximately 15 kilotons of TNT. This event clearly demonstrated that despite Earth's protective atmosphere, it remains vulnerable to collisions with celestial bodies. Asteroids and comets that cross the orbit of our planet can vary greatly in size. Scientific research shows that there are more than 1 million objects in the solar system, with sizes ranging from 10 meters to a kilometer. Each of these objects can carry destructive potential. For instance, an asteroid with a diameter of 500 meters could cause global catastrophes, altering the climate on Earth and destroying large ecosystems. These objects periodically approach Earth at dangerous distances. In 2019, astronomers detected more than 80 asteroids that crossed the orbit of our planet at a distance of less than 2 million kilometers. Although this distance may seem substantial, it is relatively small on a cosmic scale, allowing asteroids to unpredictably change their orbits under the influence of Earth's or other planets' gravitational fields. Moreover, asteroids can alter their trajectories due to interaction with solar radiation, a phenomenon known as the Yarkovsky effect. These factors make predicting their movement a complex task. For example, NASA monitors potentially hazardous objects using radio telescopes and optical systems to determine their sizes, compositions, and orbital parameters. There are even international initiatives aimed at identifying and tracking such objects, including programs developed under the auspices of the United Nations. In 2020, a group of experts on planetary defense was established to develop strategies for preventing collisions with Earth. It is important to understand that the planet moves along its orbit at a speed of around 177,000 kilometers per hour, constantly interacting with celestial bodies that are not always predictable or controllable. From a geological perspective, Earth has already experienced large-scale collisions with asteroids. One of the most famous events occurred around 60 million years ago, when an asteroid with a diameter of 10 kilometers caused a mass extinction that led to the disappearance of dinosaurs. Such events remind us that Earth is not an isolated world, but part of a vast cosmic mechanism that can suddenly change our reality. Objects orbiting in near-Earth space can have not only destructive potential, but also serve as resources for future space research. Some asteroids contain metals, such as nickel and platinum, which could be valuable to humanity in the future. For example, the asteroid Bennu, which was studied by the OSIRIS-REx spacecraft, may contain carbon compounds that are important for life and can help in understanding the formation of planets. Therefore, the constant presence of asteroids and comets in near-Earth space creates a unique context for the existence of our planet, reminding us that we live in a dynamic and sometimes dangerous environment where every detail matters. It is important to consider that even the smallest objects can have significant consequences for our civilization. Astronomers worldwide actively participate in programs for detecting and cataloging near-Earth objects, utilizing modern telescopes and algorithms. For instance, in the United States, the NEOWISE program, launched in 2009, uses an infrared telescope to detect asteroids that may be too faint to be seen with visible light. This space telescope has discovered more than 30,000 objects, including 12,000 new asteroids. Methodically scanning the sky, astronomers employ automated algorithms that help quickly identify moving objects. Such algorithms, like Pan-STARRS developed in Hawaii, have detected more than 1 million objects, including comets and asteroids, in just a few years of operation. Each discovered object undergoes an orbit calculation process, which determines how close it can approach Earth. This is done using data on the object's previous positions, which are compared with current observations. Thus, astronomers use the parallax observation method to accurately calculate the distance to objects, and their movement is tracked using specialized programs that analyze data from various telescopes. The potential danger of each discovered astronomical object is assessed on the Torino scale, where objects receive scores based on the likelihood of a collision with Earth. For example, asteroid Apophis, discovered in 1999, was initially considered a high-risk object, but further observations reduced this risk to zero for the next few decades. International cooperation plays a crucial role in this process. Within the framework of the Minor Planet Center, managed at Harvard University, astronomers from different countries exchange data on their discoveries, allowing for a more comprehensive picture of near-Earth objects. For example, in 2020, scientists from various countries united their efforts to create a global network of telescopes that enables round-the-clock observation of the sky and quick response to potential threats. These data not only help in the discovery of new objects, but also in assessing their potential danger. Programs for detecting near-Earth objects are actively developing, and today more than 30,000 asteroids are known to pass near Earth, of which more than 1,000 are classified as potentially dangerous. Kinetic impactors represent one of the most discussed methods of protecting Earth from asteroid threats. This approach involves launching specialized spacecraft that collide with threatening asteroids at high speeds, altering their trajectory. In 2020, NASA conducted successful tests of the Double Asteroid Redirection Test (DART) program, which was launched in November 2021. The DART spacecraft changed the orbit of the Dimorphos asteroid, marking the first confirmed case of altering the course of a celestial body using a kinetic impact. A crucial aspect of such technologies is the precision of calculations. Even a small change in an asteroid's trajectory can significantly affect its future path, minimizing the risk of collision with Earth. Gravitational tuggers, although still in the early stages of development, could also play a key role in combating asteroids. This method involves using the gravitational field of a spacecraft to pull an asteroid in the desired direction over an extended period. Research shows that even a small force acting over a long time can significantly change the orbit of a large celestial body. The NASA program NEA Scout is aimed at studying small near-Earth objects using miniature satellites that could eventually become part of a gravitational tugger system. Nuclear explosions are considered as a last resort if other methods fail. The idea is to detonate a nuclear device close to an asteroid, creating a powerful explosion that changes its trajectory. This approach, of course, raises many debates, as it could potentially create fragments that could threaten Earth. However, projects like Human on the Moon, Lunar Orbital Platform Gateway, involve developing nuclear technologies that could later be adapted for asteroid defense. What is important is that humanity is on the threshold of new possibilities in the field of protecting against cosmic threats. Countries such as the United States, Russia, and countries of the European Union are actively working on creating international coordination for data exchange and joint development of protection technologies. In 2020, international exercises were held to respond to a potential asteroid threat, involving more than 30 countries, discussing scenarios for dealing with potential threats. An important element of these exercises was the simulation of the interaction of various space agencies, highlighting the need for joint efforts to achieve effective protection. Strategies for protecting against asteroids show that humanity is moving towards an active role in shaping its cosmic environment. We are no longer passive victims of space, but active participants. This transition from a passive to a proactive approach to planetary protection will not only help preserve life on Earth, but also expand the horizons of research and space exploration. Astronomers and engineers continue to explore new methods, and perhaps in the next few decades, we will see the first successful mission aimed at preventing a collision with a threatening asteroid. Each new discovery in the field of astrophysics and technologies opens up new horizons for future research and possibilities. There are plans to create multifunctional space stations that could serve as bases for future missions to protect against asteroids. In particular, NASA and ESA, European Space Agency, are considering the possibility of creating a habitable module on the Moon for conducting scientific experiments that could help in the development of protection technologies. In 2023, projects were presented that involve using lasers to change the trajectory of asteroids, which also attracts the interest of researchers. Each new proposal and each new technology brings humanity closer to creating a protection system that can handle potential threats from space. International cooperation in the field of planetary defense is becoming increasingly important, as the threat from asteroids and comets requires united efforts from countries around the world. In 2016, a declaration on joint work in the field of observation of near-Earth objects was signed, involving more than 30 countries, including the United States, Russia, Japan, and the European Union. One of the key organizations dealing with this issue is NASA, which, within its Near-Earth Object Observations program, allocated more than $100 million for the funding of observations and analysis of potentially dangerous objects. In 2020, NASA and the European Space Agency, ESA, launched a joint project called AIDA, aimed at studying the binary asteroid system Didymos and its satellite Dimorphos. This cooperation includes the DART mission from NASA and the HERA mission from ESA, which are intended to help understand the possibility of deflecting asteroids from their collision course with Earth. Data exchange between countries has become critically important, as timely information about the movement and characteristics of asteroids can save millions of lives. For example, in 2020, the United Arab Emirates created a Center for the Observation of Near-Earth Objects, which actively cooperates with other international agencies such as JAXA and ESA for data collection and analysis. Within this initiative, regular international conferences are held, where scientists and researchers discuss new technologies and methods for asteroid detection. On February 18, 2020, a conference was held in Tokyo, where more than 150 scientists from different countries agreed on an action plan to improve the system for detecting and monitoring threatening objects. Space threats are becoming a factor that unites humanity, forcing it to overcome political disagreements for the sake of common security. In 2020, the UN General Assembly adopted a resolution calling for international cooperation in the field of planetary defense, which once again emphasizes the global approach to solving this problem. In parallel, within the framework of the United Nations Office for Outer Space Affairs, UNOOSA, recommendations are being developed for the integration of planetary defense into the national security strategies of countries. As a result of these efforts, international working groups are being created, which develop standards and protocols for joint actions in case of the discovery of a potentially dangerous object. In 2021, the G20 countries discussed the possibility of creating a global early warning system for asteroid threats, which became an important step towards forming a common front in the fight against cosmic threats. Space threats require united efforts, and it is in this context that it is necessary to continue developing international cooperation and data exchange to ensure the safety of all Earth's inhabitants. Scientific research shows that more than 90% of potentially dangerous objects remain unexplored, highlighting the need to expand observations and coordinate actions at the international level. The process of tectonic plate movement on Earth is a fundamental factor in the formation of supercontinents. Over the past billion years, continents have repeatedly united and separated due to this movement. According to geologists, tectonic plates move at a speed of 1 to 10 centimeters per year. This means that in tens of millions of years, as tectonic processes continue, we can expect the continents to unite again, forming a new supercontinent. For example, in the past, there was a supercontinent called Pangaea, which formed around 300 million years ago and began to break apart around 200 million years ago. The joining and separation of continents in geological history has occurred many times, and each process took millions of years. Tectonic plates, like giant mosaics, smoothly move across the Earth's mantle, and their interaction leads to the formation of new mountain systems, changes in ocean basins, and the creation of new ecosystems. An example of this is the formation of the Himalayas, which resulted from the collision of the Indian and Eurasian plates, a process that began around 50 million years ago. This process will not end with the disappearance of humanity. It will continue, creating new geographical forms on the planet. Research shows that in approximately 100 million years, new continents may emerge, united into a single whole, as has happened in the past. These changes occur independently of human activity and emphasize the infinity and continuity of geological processes. Tectonic movements that cause earthquakes and volcanic eruptions are part of this natural cycle, and their effects are felt over millions of years. Modern technologies and methods, such as satellite laser interferometry, allow scientists to more accurately track plate movements and predict possible changes. These studies help us understand what Earth will look like in the future. Scientific data show that as a result of such processes, new oceans and continents may form, with completely different climatic and ecological conditions. For example, tectonic processes in the Atlantic Ocean continue to widen it, leading to changes in the climate of neighboring regions. Thus, the movement of tectonic plates shapes not only the landscape, but also the ecosystems that will exist in the future. Scientific conclusions confirm that such changes are not a one-time event, but an eternal process that continues its work, even when humanity disappears. Tectonics is not only the key to understanding the past of Earth, but also to predicting its future. Approximately 250 million years from now, continents are expected to reconnect into a single landmass, forming a supercontinent known as Ultima Pangaea. This model is based on current studies of plate tectonics and the movement of continents. The supercontinent will occupy a central position on Earth, likely close to the equator. As a result of this positioning, the climate on Ultima Pangaea will be extremely continental, particularly in the central regions far from the sea. Temperatures in these interior areas may reach extreme values in both hot and cold seasons, creating complex ecosystems where survival will depend on the adaptation of flora and fauna. Along the edges where the land meets the ocean, the climate will be more moderate, creating conditions for diverse life. It is expected that extensive tropical forests will spread along the coasts of Ultima Pangaea, while in the more northerly and southerly regions, life forms will be adapted to colder conditions. Scientific research shows that such supercontinents have formed in the past, and their study helps us understand how climate conditions and ecosystems will develop in the future. For example, the existence of Pangaea, which existed around 300 million years ago, led to the formation of large coal reserves and changes in the biosphere. On Ultima Pangaea, it is expected that the interior regions will be inhabited by large herbivorous animals that can survive in conditions of extreme temperature changes, while on the coasts there will be smaller species that can cope with changes in sea level. Possible geographical features, such as mountain ranges formed by the collision of plates, will play a significant role in shaping the climate, creating barriers for winds and influencing rainfall. Complex systems of rivers and lakes may arise due to the erosion of these mountains, further influencing the distribution of living organisms. Thus, the model of Ultima Pangaea not only provides interesting prospects for the future of our planet, but also serves as an important tool for studying how tectonic processes can influence climate and ecosystems over millions of years. It is important to understand that such changes occur over timescales that are difficult to imagine, and they will happen independently of human activity. Scientists such as Dr. Derek V.D. Johnson from the Institute of Geology in Oklahoma are actively researching these processes and proposing new theories based on data on the movement of continents and changes in climate. For example, modern models show that as a result of the redistribution of land and water masses, sea levels will fluctuate, which will also affect life on the planet. Scientific research on the future supercontinent continues, and each new discovery adds more details to this fascinating picture. On a hypothetical supercontinent that could form in several million years, the climate will differ sharply from the present one. Extreme seasonal temperature fluctuations are expected, with interior regions experiencing severe droughts, while coastal zones will be subject to intense monsoons. Forecasts indicate that temperatures in the center of this supercontinent could reach 45 degrees Celsius in summer months, while winter nights could drop to -20 degrees. Such a contrast will create conditions where most of the land will be unsuitable for life. Interior regions, far from oceans, will experience water shortages, leading to the formation of vast deserts. Scientific research by climate scientists such as Dr. Emily Hart from the University of California shows that under such aridity, ecosystems will rapidly degrade and many plant and animal species will disappear. Coastal zones, on the other hand, will become biodiversity hotspots due to monsoon rains that will provide sufficient water for life to thrive. It is expected that monsoons will bring more than 2 meters of rainfall per year, creating conditions for the development of tropical forests and rich ecosystems. Scientists such as Dr. Li Zhong from the Institute of Global Change in Beijing note that in these coastal areas, many unique species adapted to changing conditions may emerge. Biodiversity will be concentrated in a narrow strip along the oceans, while interior regions will remain lifeless and barren. Moreover, such climatic conditions will alter the migration paths of many animals. Mammals, birds, and insects will move in search of favorable conditions, impacting ecosystems in coastal zones. Estimates suggest that more than 30% of all terrestrial species may face extinction if they cannot adapt to the new conditions. Research indicates that many species, such as large mammals, will likely retreat to narrow strips of green vegetation along the coast, where the climate will be more tolerable. The climate on the future supercontinent could pose a significant challenge to life on the planet. A high level of carbon dioxide in the atmosphere is likely to exacerbate the greenhouse effect, contributing to global warming. Temperatures in the oceans will rise, potentially leading to further changes in weather patterns and intensifying extreme weather events such as hurricanes and floods. The projected sea level rise by the 21st century could be 1 meter, significantly altering coastal ecosystems. Thus, life on this hypothetical supercontinent will be concentrated in narrow coastal strips, where monsoon rains will create relatively favorable conditions for existence. Interior regions will present harsher conditions, unable to support complex forms of life. Research shows that biodiversity will be concentrated in these coastal zones, creating pressure on ecosystems that will have to adapt to constantly changing conditions. Scientific works, such as those by Professor David Kramer from the University of Texas, emphasize the need to study these ecosystems to understand how life can adapt to extreme climatic conditions. In such a hypothetical world, global climate change will have profound consequences for biodiversity and ecosystems on the planet. In the distant future, when humanity may disappear forever, Earth will become a place where life will continue to develop, adapting to new conditions. In such circumstances, according to the predictions of scientists like Dr. Emily Chen from the University of California, organisms will be able to fill ecological niches left vacant by human activity. For example, in conditions of rising temperatures and changes in oxygen levels, aquatic organisms such as fish and marine mammals may evolve into more resilient forms of life. There could be fish that can breathe both air and water, allowing them to explore new ecosystems and venture onto land in search of food. This is similar to how the first amphibians did more than 300 million years ago. While some terrestrial ecosystems may be devastated, others, such as tropical forests, may experience a boom in development, creating conditions for the emergence of new plant and animal species. Experts like ecologist Dr. Ricardo Martinez suggest that in such forests, plants capable of photosynthesis at low light levels may emerge, allowing them to survive in dense vegetation where ordinary plants cannot compete. This could lead to the creation of entire new ecosystems, where symbiotic relationships between organisms will become increasingly important. Bacteria and fungi capable of breaking down complex organic matter could become the main participants in these new ecosystems, providing nutrients for plants that, in turn, will serve as food for newly emerging groups of animals. Imagine that several million years after the disappearance of humans, as a result of adaptation to changing environments, there could be mammals the size of dogs, capable of nocturnal hunting and using echolocation to find food in dense forests. They would resemble modern bats, but with more developed intelligence and social structures. Or perhaps we will see the emergence of large land creatures that resemble dinosaurs, but with unique adaptations allowing them to survive in a changing climate, such as thick skin for protection against high temperatures. Research shows that life on Earth has an incredible ability to restore and evolve, even after catastrophic events. In conditions where ecosystems adapt to new climatic conditions, one can expect the emergence of completely new groups of organisms that will occupy niches previously occupied by humans. The appearance of new forms of life will be a logical continuation of the evolutionary process that has been ongoing on our planet for more than 3 billion years. They may use sources of energy that we cannot even imagine, such as geothermal energy or chemical reactions occurring in the Earth's interior. Underwater ecosystems will also evolve, creating unusual forms of life, such as soft-bodied mollusks with bioluminescent properties that will use light to attract partners or repel predators. In such conditions, as predicted by biologist Dr. Stephen Hawking, life will find ways to adapt to new challenges, creating new species that will be radically different from anything we know today. It is important to note that the history of life on Earth is full of examples where organisms have evolved in response to changes in their environment, and there is no doubt that this process will continue, creating new forms of life that will exist in a world where humanity has long become a part of history. Changes on Earth occur continuously under the influence of numerous factors, including tectonic movements, climatic fluctuations, and even solar activity. Tectonic plates, moving at a speed of several centimeters per year, form new mountains and oceans, altering the planet's landscape. For example, the Himalayas, formed as a result of the collision of the Indian and Eurasian plates, continue to grow, with their height increasing by several millimeters each year. Meanwhile, processes of erosion and weathering gradually destroy existing relief forms. Over millions of years, this leads to the emergence of plains where high mountains once stood and new mountains where plains were. Internal processes, such as volcanic activity, also play a key role in shaping the planet. For instance, the eruption of Krakatoa in 1883 led to significant changes in climate and ecosystems, and even altered sea levels in the region. On a broader timescale, events like mass extinctions have drastically altered Earth's ecosystems. At the end of the Permian period, approximately 250 million years ago, a mass extinction occurred, resulting in the disappearance of around 95% of species. These catastrophic events give rise to new biodiversity, and Earth recovers, creating new ecosystems. External factors, such as changes in solar activity, also influence climate. Scientists assert that solar cycles, occurring every 11 years, can alter the level of radiation reaching Earth's surface, which in turn affects climatic conditions. For example, during the Little Ice Age in the 17th and 18th centuries, significant cooling was observed, which may have been linked to a decrease in solar activity. Over billions of years, Earth will undergo significant changes. Oceans may disappear, and new continents may arise due to erosion and volcanic activity. It is expected that in several billion years, as the Sun exhausts its hydrogen reserves, it will begin to expand, becoming a red giant. This will result in temperatures on Earth becoming too high for life, as we know it to exist. As a result, the atmosphere will change, and oceans will start to evaporate. In this context, humanity, with its history spanning only a few tens of thousands of years, will represent a mere fleeting moment in the geological history of the planet. Such a temporal scale calls into question our understanding of time and our place in the cosmos. Earth, as a living planet, continues to evolve, and its history is an unending chain of changes occurring amidst cosmic processes that lie beyond human comprehension. Scientific research shows that Earth has experienced at least 5 mass extinctions over the past 500 million years, and each of these events marked the beginning of a new era in the history of life. These events demonstrate that Earth is not a static environment, but a dynamic system in constant motion. Different species, which have evolved as a result of these changes, leave their traces in the geological record, and the study of these traces allows us to better understand how life on the planet adapts to its surroundings. The Sun is gradually becoming brighter, and this process has serious consequences for life on Earth. Currently, the Sun's brightness is increasing by about 8% every billion years. This may seem insignificant, but over several hundred million years, this small difference in brightness could significantly raise the planet's temperature. According to scientists' estimates, in about 1 billion years, the surface temperature of Earth could reach critical levels, sufficient to cause massive evaporation of the oceans. Research shows that at around 100 degrees Celsius, catastrophic evaporation of water bodies could occur, leading to significant climate change and threatening the existence of complex life forms. By the time the Sun becomes 20% brighter, which will happen in about 2.5 billion years, most of the biosphere will be forced to retreat to the poles, where temperatures will remain more tolerable. Similar changes have been observed in Earth's history, when changes in solar radiation led to mass extinctions of species. For example, around 200 million years ago, during the Triassic period, an increase in temperature caused a mass disappearance of species, and the biosphere was reduced to the limits of polar regions. The situation is exacerbated by the fact that increased solar radiation will enhance the greenhouse effect, leading to even greater heating of the atmosphere. Scientists suggest that in 3 billion years, the Sun will become hot enough to make Earth resemble Venus, where the surface temperature reaches around 400 degrees Celsius. The oceans, which currently cover more than 7/10 of Earth's surface, could completely evaporate, leaving behind only desolate deserts. The biosphere, which is currently complex and diverse, risks becoming a mere shadow of itself, with rare forms of life capable of surviving in extreme heat conditions. Evolution, as we know, does not stand still, and the species that will exist in these conditions will be completely different from those we observe today. For example, some organisms, such as extremophiles, are already able to survive in high temperature and radiation conditions, but their adaptation does not guarantee the preservation of the complex ecosystem to which we are accustomed. Therefore, the increase in the sun's brightness is not just an astronomical fact. It is a threat that could change our entire planet and its ecosystems. Ultimately, in about 4 billion years, when the sun becomes a red giant, it will engulf the inner planets, including Earth, putting an end to all known forms of life. When the internal heat of the Earth runs out, the planet will face the end of active tectonic plate movement, which will occur approximately in 1 billion years. The decrease in temperature in the core will slow down the convective flows in the mantle, and the process that once created mountains and volcanoes will stop. Consequently, continents will stop moving, and all geological processes that shaped our landscape will cease. In this scenario, Earth will become a geologically dead planet, where erosion will gradually smooth out the relief, leaving behind only shadows of once mighty mountains. The erosion process, which is currently actively shaping our planet, will continue, but without new volcanoes and earthquakes that replenished mineral reserves and altered the landscape. Approximately 2 million years after the cessation of tectonic plate movement, significant changes will occur. The average heights of continents will begin to decrease, and oceans will gradually fill with sedimentary rocks, creating a monotonous and flat space. The relief that we know will become a mere memory of a dynamic planet, when tectonic processes created and destroyed, forming the diversity of ecosystems. Without tectonic activity, the cycle of elements necessary for supporting complex life will be disrupted. Oxygen, carbon, and other important elements will be in a state of stagnation, and the biosphere will gradually fade away. Carbon reserves that currently support life on the planet will be depleted, and new sources of carbon, such as volcanic gases, will no longer enter the atmosphere. As a result, the level of oxygen in the atmosphere will begin to decrease, leading to mass extinctions of species. Approximately 500 million years later, when the last remaining ecosystems disappear, our oceans will become dead, and the land will turn into a lifeless wasteland. Plants that once covered the earth will be displaced, and animals that depended on them will disappear. This will be a world where even traces of life will gradually fade away under the influence of time and erosion. Approximately 2 billion years later, when the Earth finally cools down, its surface will become a place where only winds will roam the lifeless plains, and rivers, once mighty, will turn into slowly flowing streams, losing their power. Water that filled the oceans will slow down, and the sea level will begin to fall, exposing new lands that were once underwater. Scientific research shows that approximately 3 billion years after the end of tectonic activity, the planet will resemble Mars, a lifeless and harsh world without water or an atmosphere suitable for life. Without tectonic activity and the circulation of elements, the life we know will disappear, leaving only geological evidence that once life thrived here. The life on Earth that we know today is a result of billions of years of tectonic processes, and when they cease, the planet will become a monument to its past. In 5 to 7 billion years, the Sun will enter the phase of a red giant, exhausting its hydrogen reserves in the core. At this stage, the star will begin to expand, growing to such an extent that its radius will be hundreds of times greater than it is now. In this process, the inner planets, including Mercury and possibly Venus, will be engulfed by the Sun's scorching layers. The temperature on the surface of the star will rise to 1,000 degrees Celsius, leading to the evaporation of Earth's oceans and the destruction of its atmosphere. Studies indicate that as a result of this process, sea levels will rise and all bodies of water on the planet will evaporate, leaving only barren landscapes and charred remnants of ecosystems. Around 2 billion years before this event, according to scientists' estimates, life on Earth will become impossible due to intense solar radiation, leading to the extinction of all forms of life that cannot adapt to the new conditions. When the Sun reaches the stage of a red giant, its light will be so bright that Earth will be illuminated by a huge red disk, occupying a large part of the sky, and the temperature on the planet will reach critical values, exceeding 200 degrees Celsius. In this atmosphere, devoid of oxygen and water, life as we know it will become impossible. The Sun, swelling to colossal size, will not only threaten Earth, but also change the entire dynamics of the solar system. Even Mars, currently far from the Sun, will feel the consequences of this expansion, as its atmosphere will also begin to disappear. Ultimately, over the course of millions of years, the Sun will lose its outer layers, expelling them into space and forming a planetary nebula. At this moment, only the star's core will remain, becoming a white dwarf. This indestructible star will remain in space for billions of years, gradually cooling and losing its brightness. The solar system, once teeming with life, will transform into a lifeless space, where its former inhabitants will be but a memory of the time when life once thrived. The entire process, from the Sun's transformation into a red giant to the formation of a white dwarf, will take approximately 10 billion years, which is but a fleeting moment in the vastness of the cosmos. The geological heritage of Earth is a vast chronicle inscribed in the layers of rock, where each page preserves information about catastrophes, climate changes, and the evolution of life on the planet. This chronicle is formed over billions of years as sedimentary rocks accumulate on the floors of oceans, rivers, and lakes, preserving traces of past epochs. For example, in layers formed around 500 million years ago, one can find fossilized remains of ancient marine organisms such as trilobites, which once inhabited the oceans. These organisms, preserved as fossils, allow us to study the biological diversity of those times and changes in ecosystems. Volcanic activity, which has been present throughout Earth's history, leaves its mark in the form of volcanic rocks and tuffs, which tell of periods of powerful eruptions. A vivid example is the layers formed as a result of the eruption of a supervolcano around 600,000 years ago, when ash and lava flows altered the landscape over many kilometers. These processes leave traces not only in geology, but also in the planet's climate. For instance, research shows that large volcanic eruptions can lead to global cooling, altering climatic conditions for decades. Geologists use radiometric dating methods to determine the age of rock formations, allowing them to trace the temporal framework of these events. For example, methods such as carbon dating can establish the age of organic remains, while uranium-lead methods can date older minerals, some of which may be up to 4 billion years old. These data provide a comprehensive picture of how Earth has evolved, how continents have changed, and how oceans have emerged and disappeared. Each layer of rock is not just a stone, it is a book recording stories of tectonic movements, sea level changes, and even major extinction events, such as the Permian extinction that occurred around 260 million years ago, when approximately 95% of all species on Earth went extinct. This catastrophe was likely caused by multiple factors, including volcanism and climate change, and its traces can be found in geological layers, allowing researchers to understand the causes and consequences of these natural disasters. The study of Earth's geological heritage opens up an entire era, where each layer is a crucial element in understanding the planet's dynamics. In this context, Earth becomes not just a planet, but a vast library, whose pages are filled with mysteries and answers to questions about our history. Each time geologists explore a new area, they are as if opening a new chapter in this endless story, gaining a unique opportunity to learn about how life and nature have changed over millions of years. In this context, one can say that Earth continues to write its history, and each new discovery provides us with a better understanding of the conditions of life, the events that shaped our world, and how it all relates to the present. Structures such as shales, sandstones, and limestones form complex histories that carry information about ancient ecosystems, climatic changes, and tectonic processes. Each of these materials, whether small deposits or large marble formations, has a unique composition that can tell us about the chemical composition of the atmosphere and oceans in different epochs. Scientific research, such as isotope analysis, helps us understand how conditions on Earth have changed and how this has influenced the development of life. As a result, the geological heritage becomes the key to unraveling many mysteries related to our planet, including understanding how humanity can adapt to the changes that are happening today. The study of ancient catastrophes requires the use of various methods that allow scientists to reconstruct the picture of events that occurred on Earth millions and even billions of years ago. One of the most powerful tools is the analysis of isotopes, which enables scientists to determine how the chemical composition of the atmosphere and oceans changed during different geological epochs. For instance, the study of carbon isotopes helps to understand how climate changes occurred due to volcanic activity or changes in the ocean's composition. paleontological data also play a significant role in understanding catastrophes. Fossils found in layers of the Earth can reveal mass extinctions, such as the event that occurred around 65 million years ago when dinosaurs disappeared. Scientists like American paleontologist David Polly study these findings to establish a link between climate changes and biological extinctions. Geophysical research, including seismic and magnetic methods, allows for the analysis of Earth's internal structure and the identification of traces of catastrophic events, such as asteroid impacts or powerful volcanic eruptions. For example, in 2006, a team of scientists led by Professor Tom Hake conducted research in the region of the Mexican Gulf and discovered traces of a massive crater formed by an asteroid impact. Modern technologies, such as satellite imagery and computer modeling, enable researchers not only to collect data, but also to visualize events that occurred millions of years ago. For instance, the use of remote sensing methods helps to study changes in landscapes caused by ancient catastrophes and assess their impact on ecosystems. Thus, through the combination of various methods and technologies, scientists can create a detailed picture of the catastrophes that shaped our planet, including their scale and consequences for life on Earth. The analysis of carbon isotopes, for example, has shown that during the mass extinction of trilobites, the level of carbon in the atmosphere sharply increased, indicating global changes. The study of geological catastrophes provides scientists with unique tools for understanding contemporary processes and predicting future events. For instance, the study of meteorite impact craters, such as the Chicxulub crater in Mexico, which formed around 65 million years ago, helps assess the potential consequences of Earth's collisions with large cosmic objects. Research has shown that this impact could have been the catalyst for the mass extinction of dinosaurs. Scientists use data from such catastrophes to model scenarios that help predict how various forms of life respond to sudden environmental changes. The restoration of climatic conditions, such as those observed during the last ice age, also plays a crucial role. Studies conducted in climate archives, such as ice cores from Greenland and Antarctica, demonstrate that rapid temperature fluctuations in the past were linked to natural processes like volcanic activity and changes in Earth's orbit. These data are important for understanding current climate changes related to human activity and contribute to the development of more effective adaptation and mitigation strategies. Volcanic eruptions, such as the eruption of Mount Tambora in 1811, also provide valuable lessons. This eruption led to global cooling, known as the Year Without a Summer, which caused famine in Europe and North America. Studying such events allows scientists to evaluate how similar phenomena could impact food security in the face of contemporary climate changes. Geological catastrophes typically leave behind clear geological traces that can be studied using radiometric dating and geophysical research methods. These methods provide precise temporal frameworks for events, allowing for the creation of a sequential picture of changes on Earth. In particular, the analysis of sedimentary layers formed as a result of floods or tsunamis gives insight into the frequency and intensity of such catastrophes. For example, research conducted on the coast of Japan has shown that sea level changes over the course of millennia are directly linked to seismic activity and climate changes. These data help predict how sea level changes will affect coastal communities in the future. Scientists also study how animals and plants have adapted to extreme conditions resulting from catastrophes, which can provide clues about how modern ecosystems might respond to upcoming changes. For instance, research conducted in the region of Madagascar has identified species that survived a series of ecological catastrophes due to their ability to adapt to changing conditions. This discovery underscores the importance of preserving biodiversity, as various species can play a key role in the resilience of ecosystems. As climate changes become increasingly evident, the study of geological catastrophes is not just a scientific interest, but a practical necessity. Research shows that Earth's history is full of lessons that can guide us in choosing methods of adaptation and mitigation. One such catastrophe, a flood that occurred around 13,000 years ago, left traces that we can observe today. These catastrophes remind us of the fragility of our planet and the importance of being prepared for the unexpected. Understanding how Earth reacted to past catastrophes helps us better prepare for future challenges. There are specific examples where predictions based on the analysis of historical data on catastrophes have helped prevent serious consequences. For instance, in 2000, a strong earthquake was predicted in Chile based on the study of historical data and seismic activity. This allowed local authorities to prepare and minimize damage. Research also shows that quick response to natural catastrophes can save lives, based on lessons learned from past events. For example, the tsunami warning system was developed after the 1999 tsunami in the Indian Ocean, which claimed thousands of lives. This system, based on data from past catastrophes, allows for effective warning of the population about potential threats. Geological catastrophes, such as volcanic eruptions or earthquakes, do not merely destroy ecosystems and human settlements, but also raise profound philosophical questions about humanity's place in the universe. These catastrophes remind us of the fragility of life and our role as a small part of a vast, unforgiving planet. For instance, the famous eruption of Krakatoa in 1883 not only caused significant destruction, but also led to global climatic changes, lowering temperatures by several degrees Celsius for several years. This event demonstrated how planetary forces can dramatically alter the conditions of life on Earth. The realization that life on the planet is subject to random and unpredictable catastrophes forces us to re-evaluate our understanding of progress and evolution. Throughout history, humanity has faced numerous such events, including mass extinctions, such as the extinction of the dinosaurs around 65 million years ago, when a catastrophic asteroid impact led to the disappearance of more than 70% of all species on Earth. This makes us ponder the interplay between chance and necessity in the process of evolution. Our ancestors, who survived such catastrophes, adapted to the changed conditions, leading to the emergence of new species and, ultimately, the development of humans. Human history is also filled with examples where wars and natural disasters led to social changes and new technological advancements. For example, World War I, which arose from political conflicts and economic crises, can also be seen as a catastrophe that changed the course of history and brought about significant social changes. Understanding the instability of our existence underscores the importance of preparation and adaptation, which is also relevant to contemporary challenges such as climate change. A person who recognizes their vulnerability in the face of nature's power begins to value life more and strives for harmony with the surrounding world. This changes our perception of humanity's role on the planet and makes us consider how we can survive and develop in the face of constant risk. Geological catastrophes show that life is not guaranteed and that progress can be destroyed in an instant. For example, the aftermath of the earthquake in Japan in 2011 showed how a highly developed country could be on the brink of catastrophe due to natural forces. This underscores the need to rethink our approach to technology and natural resources, as they may prove insufficient in the face of natural disasters. The realization of the fragility of life and the constant threat posed by geological processes makes us approach questions of ecology, sustainable development, and technological innovations more deliberately. Ultimately, understanding that we live on a planet where geological catastrophes can occur at any moment prompts us to act more responsibly and strategically, creating resilient communities capable of facing these challenges. Scientific research shows that such catastrophes as volcanic eruptions or earthquakes can recur with a certain periodicity, making their prediction and preparation critically important. For example, research shows that strong earthquakes in California occur approximately every 160 years, making preparation for them vital for the preservation of life and property. Volcanic eruptions, meteorite impacts, and other catastrophic events throughout Earth's geological history not only destroyed, but also opened new horizons for life. An example is the Permian extinction that occurred around 250 million years ago, when approximately 90% of all species on the planet disappeared. While this event was a catastrophe, it also served as a catalyst for the evolution of dinosaurs, which dominated the subsequent Mesozoic era. Dinosaurs, in turn, evolved into various forms, from small feathered creatures to giant land, air, and water predators. The destruction of ecosystems caused by such catastrophes created space for new species that adapted to the changed conditions. For instance, after the extinction of dinosaurs around 60 million years ago, mammals began to occupy the ecological niches left by their predecessors. At this time, primates, the ancestors of modern humans, and other groups emerged, leading to the diversity of life forms we observe today. Thus, each catastrophe, though terrible, becomes a catalyst for change, driving evolutionary breakthroughs and renewal. For example, extensive forest fires that occurred in the past created open spaces, fostering the growth of new plants and the creation of new ecosystems. Simultaneously, catastrophic floods could transport seeds over long distances, allowing them to germinate in new places and thereby contributing to biodiversity. Each end of old forms of life, therefore, becomes a beginning of new evolutionary experiments. Looking at Earth's geological history, scientists estimate that the planet has experienced more than 5 mass extinctions, each leaving its mark on the evolutionary development. These events demonstrate that life on our planet is not static, but constantly changes and adapts to new conditions. Processes such as plate tectonics cause the formation of new mountain ranges and oceans, creating new ecological niches and allowing life to develop in unexpected directions. This continuous interaction between catastrophes and evolution underscores the cyclical and dynamic nature of life on Earth. With each new geological layer, we see life recovering, adapting, and flourishing, despite the destructions that threaten it at every turn. In this endless game of life and death, destruction becomes creative, and vice versa, over billions of years. Ultimately, every end becomes a beginning of something new, and looking at our planet, we understand that chaos and order go hand in hand. Good night, and may your dreams be filled with images of ancient catastrophes and rebirths, creating new amazing worlds where each ending is merely a prelude to a new beginning.